Tonight we drift into the story of pulsars, those cosmic lighthouses spinning in the darkness between stars. These are neutron stars, the collapsed hearts of giant suns, spinning hundreds of times each second while beaming radiation across the galaxy. From a graduate student's curious discovery in 1967 to their role in detecting ripples in space-time itself, pulsars have transformed our understanding of physics, gravity, and the universe's most extreme environments. Settle in somewhere comfortable as we explore their entire remarkable story. The summer of 1967 was unremarkable in many ways. Students across England prepared for examinations, worried about their futures, and wondered what their research might reveal. At Cambridge University, a young graduate student named Jocelyn Bell spent her days analysing mountains of paper charts that spooled endlessly from a peculiar radio telescope. She had helped build this instrument herself, hammering posts into muddy fields and soldering connections under grey skies. The telescope wasn't designed to be elegant. It sprawled across acres of farmland, a forest of wires and poles that looked more like an abandoned electrical project than a cutting-edge scientific instrument. The telescope's purpose was straightforward enough. Bell's supervisor, Anthony Hewish, wanted to study quasars, those distant brilliant objects that had only recently been discovered. Quasars flickered and twinkled as their radio signals passed through the turbulent solar wind, and Hewish believed that by studying this scintillation, they could learn something profound about these mysterious sources. Day after day, the telescope recorded signals on long strips of chart paper, more than 30 meters unwinding each day. And day after day, Jocelyn Bell examined every inch of those recordings by eye, searching for the telltale signs of quasar scintillation. It was tedious work. Most of what she saw was exactly what you'd expect. The occasional spike from a passing aircraft, interference from Earth-based radio sources, the steady hum of cosmic noise. But in late July, Bell noticed something peculiar. A tiny bit of scruff on the chart recordings, no more than a quarter-inch of unusual signal among millions of inches of paper. It appeared in recordings from a specific patch of sky, and when she looked back through older charts, she found it had appeared before. Not always, not consistently, but when it was there, it occupied the same position among the stars. This was curious behavior. Man-made interference would wander across the sky as the Earth rotated. Signals from satellites would move. Even the scintillation from quasars would vary in a particular way depending on the solar wind. But this signal kept its place in the heavens, suggesting it came from something fixed out there among the stars. Bell mentioned it to Hewish, who suggested they needed better recordings. They switched to a faster chart recorder that could capture more detail, and then began the waiting game. For a month nothing happened. The fast recorder ran continuously, churning out detailed charts, but the mystery signal remained absent. Bell continued her normal survey work, probably wondering if she'd imagined the whole thing, or if it was just a fluke. Then, on November 28th, the signal returned. But this time, with the faster recorder running, they could see it clearly. The scruff wasn't random noise or a blob of interference. It was a train of pulses, perfectly regular, arriving every 1.337 seconds. Pulse, 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 pulse. Like a cosmic heartbeat, steady and unwavering. Nothing like this had ever been seen before. No known astronomical object produced such regular pulses. Stars varied in brightness, but over days or months, not seconds. Even the most rapidly pulsating stars had periods measured in hours. For something to pulse this quickly and this regularly seemed almost impossible. The discovery was so unexpected, so strange, that Bell and Hewish had to consider possibilities that seemed almost absurd. The team jokingly dubbed the source LGM-1 for Little Green Men. The nickname was humorous, but the underlying question wasn't entirely silly. Could these pulses be artificial? Could they be signals from an extraterrestrial civilization? The regularity was almost eerie. If you wanted to announce your presence to the cosmos, a perfectly regular beacon would be a good way to do it. Bell and Hewish found themselves facing a fascinating philosophical question. What does one do if one thinks they might have detected alien intelligence? Announce it immediately and risk being spectacularly wrong, remain silent and potentially sit on the most important discovery in human history? The answer came within weeks. Bell found another source of pulses, this one in a completely different part of the sky, pulsing with a different period. Then another. Then a fourth. 4 separate sources, each with its own period, each keeping perfect time. The little green men hypothesis quietly faded away. No one seriously believed that 4 separate civilizations would all be broadcasting at Earth with slightly different periods. These had to be natural astronomical objects, something the universe was producing on its own. But what? The discovery paper appeared in the journal Nature on February 24, 1968. It was cautious, scientific, and understated in the way that good scientific papers often are. The sources were designated as pulsating radio sources, quickly shortened to pulsars. The paper noted their extraordinary regularity and speculated that they might be related to neutron stars, those theoretical objects that had been predicted decades earlier but never observed. The astronomical community responded with immediate excitement. Within months, radio telescopes around the world were searching for more pulsars, and they found them everywhere. The Parkes Radio Telescope in Australia made its first pulsar observation in 1968. The discovery was so significant that the Parkes telescope and a pulsar signal would later appear on Australia's $50 note, a rare honour for a scientific instrument. More pulsars appeared week by week. Each had its own period, its own personality. Some pulsed several times per second, others more slowly, but all shared that remarkable regularity that had first caught Bell's attention on those chart recordings. By year's end, dozens of pulsars had been catalogued. The discovery had opened an entirely new window on the universe. Here were objects that didn't fit into any existing category. They weren't ordinary stars. They weren't white dwarfs. They weren't quasars or galaxies. They were something new, something that required new physics to explain. And as astronomers studied them more carefully, they began to realize that these pulsars were providing clues to one of the most extreme states of matter imaginable. The connection to neutron stars solidified when astronomers discovered a pulsar right in the center of the Crab Nebula, the expanding cloud of gas left behind by a supernova explosion that Chinese astronomers had recorded in the year 1054. The Crab pulsar spun 30 times per second, far faster than any star could possibly rotate without tearing itself apart. Only something incredibly small and incredibly dense could spin that quickly. Only a neutron star could maintain such rotation without flying apart. The pieces of the puzzle clicked into place. In 1974, the Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle for their work in radio astronomy, with the prize specifically noting Hewish's decisive role in the discovery of pulsars. Jocelyn Bell did not share the prize, a decision that sparked considerable controversy. Many felt, and many still feel, that Bell deserved recognition for making the initial observation that led to this revolutionary discovery. Bell herself handled the situation with remarkable grace, pointing out that as a graduate student, she wasn't expected to share such honours, and emphasizing that the discovery led to exciting new science regardless of who received credit. The controversy aside, the impact of the discovery was undeniable. Pulsars had arrived and they would transform astrophysics. They provided the first direct evidence that neutron stars existed. They offered new ways to test Einstein's theory of general relativity. They became tools for studying the interstellar medium, for measuring cosmic distances, for probing the extreme physics that occurs when gravity becomes overwhelmingly strong. From a bit of scruff on a graduate student's chart recordings, an entire field of research had emerged. The cosmic lighthouses were flashing their beams across the galaxy, and humanity had finally learned to see them. To understand what a pulsar truly is, we need to journey into the realm of the extremely small and the unimaginably dense. Picture a star like our Sun, a vast sphere of hot plasma held together by its own gravity. The Sun is large enough that more than 1 million Earths could fit inside it, and it will shine for billions of years, steadily fusing hydrogen into helium in its core. But pulsars are nothing like this. A pulsar is what remains after a much more massive star has died, and its death is anything but peaceful. A pulsar is a neutron star, and a neutron star is perhaps the most extreme object in the observable universe short of a black hole. Take the mass of 1.5 suns, all that matter, all that material, and compress it into a sphere just 20 to 30 kilometers across. That's smaller than many cities here on Earth. London, New York, Tokyo, any of these urban sprawls are larger than a neutron star. Yet that tiny sphere contains more mass than our entire sun. The resulting density is almost incomprehensible. If you could somehow take a teaspoon of neutron star material and bring it to Earth, that teaspoon would weigh about 1 billion tons. A single sugar cube of neutron star matter would weigh as much as all of humanity combined. This isn't a metaphor or an exaggeration. This is the actual calculated density of these objects. They are so dense that their gravity warps space and time around them in ways that are measurable and profound. Light bends as it passes near them. Time itself runs more slowly at their surface than it does far away in the emptiness of space. The material inside a neutron star is unlike anything we can create or easily study on Earth. In the outer crust, atoms are crushed together so tightly that electrons are pushed into the atomic nuclei, combining with protons to form neutrons. The star is supported not by normal atomic forces, not by the electromagnetic repulsion that keeps ordinary matter from collapsing, but by something called neutron degeneracy pressure. This is a quantum mechanical effect, a consequence of the fact that neutrons, like electrons, obey the Pauli exclusion principle. You can't squeeze an infinite number of neutrons into an arbitrarily small space. Eventually they resist, and that resistance is what holds a neutron star up against its own crushing gravity. Deeper inside, the physics becomes even more exotic. The neutrons may form strange states of matter, perhaps even breaking down into their constituent quarks. These are still theoretical ideas, the subject of ongoing research and debate. We simply don't know for certain what happens at the very center of a neutron star, because we can't reproduce those conditions in our laboratories. The densities are too high, the pressure's too extreme. Neutron stars are, in a sense, natural laboratories, showing us what matter does when pushed to its absolute limits. But density alone doesn't make a pulsar. What makes a pulsar detectable, what produces those regular pulses that Jocelyn Bell saw on her chart recordings, is the combination of rapid rotation and an intense magnetic field. Neutron stars spin, not slowly, like the Earth turning once per day, but incredibly rapidly. The fastest known pulsars spin more than 700 times per second. Even a relatively slow pulsar might complete a rotation once per second. This is extraordinary when you remember that the object spinning is as massive as the Sun. The reason for this rapid rotation is a matter of conservation of angular momentum. The original star, before it collapsed, was rotating. Perhaps slowly, perhaps taking weeks or months to complete one rotation. But when the core collapsed down to neutron star size, it retained most of that rotational motion. And because the radius shrank so dramatically, the rotation rate increased enormously. It's the same principle that causes a figure skater to spin faster when they pull their arms in close to their body. The neutron star is the ultimate cosmic figure skater, spinning with an angular velocity that would tear any ordinary object to pieces. The magnetic field adds the final ingredient. Neutron stars have magnetic fields that are trillions of times stronger than Earth's magnetic field. These fields are so intense that they affect the very structure of atoms, elongating electron clouds into cigar shapes and creating conditions that have no parallel in terrestrial experience. The origin of these fields is still debated, but they likely arise from the compression and concentration of the original star's magnetic field during the collapse process. Whatever their origin, they dominate the physics near a pulsar's surface. These magnetic fields aren't aligned with the pulsar's rotation axis. Picture a bar magnet spinning at an odd angle, and you'll have the basic idea. As the neutron star rotates, its magnetic field rotates with it. This creates an electric field at the star's surface, strong enough to rip particles away from the solid crust and accelerate them to nearly the speed of light. These particles, electrons and positrons mostly, stream away from the magnetic poles in focused beams. As they spiral along the magnetic field lines, they emit radiation, radio waves, visible light, X-rays, gamma rays. These beams of radiation are what we detect as pulses. The lighthouse analogy is almost perfect. Imagine a lighthouse on a rocky coast, its beams sweeping in circles through the darkness. Ships only see the light when the beam points in their direction. The rest of the time, from their perspective, the lighthouse is dark. A pulsar works the same way. The beams of radiation sweep around as the star spins, and we only see a pulse when one of those beams happens to point toward Earth. If the beams don't intersect our line of sight, we might never know the pulsar exists. There could be neutron stars out there, spinning and beaming radiation into space, completely invisible to us simply because their beams don't happen to point our way. This explains the pulsar's regularity. The neutron star is spinning with a period determined by its mass, radius, and angular momentum. These quantities change very slowly over time, so the rotation period is extraordinarily stable. Pulsars are among the most accurate natural clocks in the universe. The best of them keep time better than the finest atomic clocks humans have built. Astronomers can predict when the next pulse will arrive to within microseconds, sometimes nanoseconds, over years of observations. Not all pulsars pulse at radio wavelengths. Some emit primarily in X-rays or gamma rays. Some pulse in visible light. The Crab pulsar flashes in almost every wavelength we can detect, from radio waves to gamma rays. The radiation mechanism differs slightly depending on where in the magnetosphere the particles are being accelerated, but the basic principle remains the same. Particles stream along magnetic field lines, emit radiation, and that radiation sweeps across the sky as the star rotates. Over time, pulsars slow down. They lose rotational energy as they beam radiation into space, and as they stir up the surrounding interstellar medium through their magnetic fields. This spin-down is measurable. Astronomers can detect the gradual lengthening of a pulsar's period over years of observations. For a typical pulsar, the period increases by perhaps 1/millionth of a second per year. That might not sound like much, but it's enough to allow astronomers to calculate how much energy the pulsar is losing and to estimate how old it is. A young pulsar, freshly formed in a supernova explosion, spins rapidly and has a strong magnetic field. Over millions of years, it gradually slows down. The magnetic field weakens, though we don't fully understand why. The pulsar becomes less energetic. Its beams weaken, and eventually it slows to the point where it can no longer accelerate particles effectively. The lighthouse turns off. The pulsar becomes a dead neutron star, still spinning in the darkness, but no longer producing detectable beams. This is the fate of most pulsars, to fade into silence after perhaps 10 million years. But there's a twist to this story, a way for old, dead pulsars to be brought back to life. If a neutron star happens to be in a binary system with another star, matter can flow from that companion onto the neutron star. This accretion of material can spin the neutron star back up, recycling it into a new kind of pulsar. These millisecond pulsars, as we'll explore later, are among the most fascinating objects in the sky. They're the cosmic equivalent of taking an old worn-out spinning top and giving it a new, vigorous spin. The study of pulsars has revealed a universe far stranger than earlier generations could have imagined. These are objects where a teaspoon of matter weighs 1 billion tons, where magnetic fields distort the fabric of space itself, where gravity is so strong that general relativity isn't just a small correction, but the dominant description of reality. They are stellar lighthouses marking the locations of nature's most extreme laboratories, places where matter behaves in ways we're still working to understand. From a peculiar signal on a chart recording to a new window on fundamental physics, pulsars have shown us that the universe is endlessly inventive, always capable of surprising us with phenomena that push the boundaries of what we thought possible. Every pulsar begins its existence in violence. The story of a pulsar's birth is inseparable from the story of stellar death, specifically the death of massive stars in supernova explosions. To understand where pulsars come from, we need to follow the life cycle of a star far more massive than our Sun, from its formation in clouds of gas to its spectacular final moments. Stars form when clouds of gas and dust in interstellar space collapse under their own gravity. As the cloud contracts, it heats up, and if it's massive enough, The temperature and pressure at its center eventually become high enough for nuclear fusion to begin. Hydrogen atoms slam together, fusing to form helium and releasing tremendous amounts of energy in the process. This energy creates an outward pressure that balances the inward pull of gravity, and the star settles into a stable equilibrium that can last for millions or billions of years. Our Sun is a relatively lightweight star, and it will spend about 10 billion years in this hydrogen-burning phase. When it eventually runs out of hydrogen in its core, it will swell into a red giant, fuse helium into carbon and oxygen, and ultimately shed its outer layers to become a white dwarf. That will be the end of its story, but stars much more massive than the Sun, those with initial masses of 8 solar masses or more, follow a different, more dramatic path. A massive star burns through its fuel much faster than a lightweight star. Its higher mass means stronger gravity, which means higher temperatures and pressures in the core, which means faster fusion. A star 20 times the mass of the Sun might exhaust its hydrogen fuel in just a few million years, a cosmic eye blink compared to the Sun's 10 billion year lifetime. But the story doesn't end when the hydrogen runs out. The massive star's core contracts, heats up further, and begins fusing helium into carbon and oxygen. Then carbon fuses into heavier elements, then neon, then oxygen, then silicon, building up a layered structure with different fusion reactions happening in different shells. This process continues until the core is primarily iron. Iron is special. It's the most stable nucleus, the endpoint of fusion. Fusing iron into heavier elements doesn't release energy, it consumes energy. When a massive star builds up an iron core, it has reached the end of the line. There's no more fuel to burn, no more fusion reactions that can provide energy to support the star against gravity. The core has grown to perhaps 1.5 times the mass of the Sun, all of it iron and nickel, hot but no longer generating energy from fusion. What happens next occurs with terrifying speed. The iron core can no longer support itself. Electron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs, isn't strong enough to hold up a core this massive. The core collapses, not gradually, not over millions of years, but in less than a second. The center of the star, a region with the mass of the Sun, plummets inward, accelerating to 1/4 of the speed of light. Atoms are crushed. Electrons are forced into nuclei, combining with protons to form neutrons. The collapsing core becomes a fluid of neutrons. The collapse continues until the density reaches nuclear density, the density of an atomic nucleus. At this point, neutron degeneracy pressure finally kicks in. The neutrons resist being compressed further, and the collapse halts. But the halting is not gentle. The infalling material rebounds like a rubber ball dropped onto a hard surface, but on a cosmic scale. A shock wave blasts outward from the core at tens of thousands of kilometers per second. This shock wave tears through the star's outer layers, heating them to billions of degrees and blowing them into space. The star has become a supernova, briefly shining with the light of 1 billion suns. For a few days, a single supernova can outshine an entire galaxy. The explosion is visible across cosmic distances. If a supernova occurred in our galaxy, close enough to Earth, it could be visible during daytime, casting shadows at night. Historical records describe such events. Chinese astronomers observed the supernova that created the Crab Nebula in 1054. European astronomers saw Tycho's supernova in 1572 and Kepler's supernova in 1604. These were extraordinary events, guest stars appearing where no star had been before, sometimes outshining everything else in the sky. The explosion disperses most of the star's mass into space, enriching the interstellar medium with heavy elements forged in the star's core and in the explosion itself. The oxygen in the air you breathe, the carbon in your cells, the iron in your blood, all of these elements were created in stars and scattered by supernovae. We are quite literally made of stardust, the ashes of stars that died long before our sun was born. But not everything is blown away. The core remains, compressed down to neutron star density. What was once the central region of a massive star, several 100,000 kilometers across, is now a sphere 20 kilometers wide. That sphere is spinning rapidly, its rotation inherited from the original star but sped up enormously by the collapse. and it has an intense magnetic field, either preserved and amplified from the original star's field or generated by some process during the collapse itself. The newborn neutron star finds itself at the center of an expanding cloud of debris, the remnant of the supernova explosion. This debris continues to glow from the heat of the explosion and from radioactive decay of elements created in the blast. Over thousands of years, the debris expands and cools, eventually becoming invisible to optical telescopes but still detectable in radio waves and X-rays. These are supernova remnants, and they're scattered throughout our galaxy. And at the heart of many supernova remnants, it's a pulsar. The connection between pulsars and supernovae was confirmed dramatically when astronomers found a pulsar in the Crab Nebula. The Crab Nebula is the remnant of that 1054 supernova, still expanding more than 900 years later. At its center spins the Crab pulsar, rotating 30 times per second, beaming energy into the surrounding nebula. The energy from the pulsar's rotation powers the nebula's glow, explaining why the Crab Nebula continues to shine so brightly nearly a millennium after the explosion that created it. The discovery of the Crab pulsar in 1968 was crucial. Its 30-millisecond period was far too fast to be explained by any model other than a spinning neutron star, and its location, precisely at the center of a known supernova remnant, confirmed the connection between neutron stars and supernovae that physicists had predicted. Here was direct evidence that the wild theoretical predictions of the 1930s that neutron stars would form in supernova explosions were correct. More young pulsars have been found in supernova remnants since then. The Vela pulsar sits in the Vela supernova remnant, spinning 89 milliseconds per period. PSR 0538 plus 28117 resides in the remnant known as Simys 147, also called the Spaghetti Nebula for its tangled filamentary structure. Each of these pulsars is young in astronomical terms, perhaps only thousands of years old, still energetic and rapidly spinning because they were born relatively recently. Not every supernova leaves behind a pulsar. If the core is too massive, even neutron degeneracy pressure can't stop the collapse, and the result is a black hole instead of a neutron star. The dividing line seems to be around 2 to 3 solar masses for the remaining core. Lighter cores become neutron stars. Heavier cores collapse completely into black holes. And not every neutron star becomes a visible pulsar. The geometry has to be right. The magnetic field has to be strong enough, and its orientation has to be such that at least one of the beams sweeps across Earth. We may be missing many neutron stars simply because their beams point in other directions. The formation of a neutron star is also accompanied by an enormous release of neutrinos. When the core collapses and electrons are forced into nuclei to form neutrons, each combination of an electron with a proton produces a neutrino. Trillions upon trillions of neutrinos are created in a fraction of a second, carrying away most of the energy released in the collapse. These neutrinos stream outward, barely interacting with matter racing away at the speed of light. They can pass through the entire star, through the Earth, through almost anything without stopping. In 1987, astronomers witnessed a supernova in the Large Magellanic Cloud, a nearby dwarf galaxy. Supernova 1987A was the closest supernova to Earth in nearly 400 years, close enough that neutrino detectors in Japan and the United States detected a handful of neutrinos from the collapsing core. Only about 20 neutrinos were caught, out of the unimaginable number released, but those 20 neutrinos confirmed the theoretical models of core collapse. The neutrinos arrived before the visible light from the supernova as expected, because the neutrinos escaped immediately while the light had to fight its way through the collapsing star. This was the first time neutrinos from beyond our solar system had been detected, a remarkable achievement. Supernova 1987A was expected to leave behind a neutron star, but despite extensive searches, no pulsar has been definitively detected at its center. Perhaps the beams don't point toward us. Perhaps the neutron star is surrounded by dense material from the explosion that blocks its emission. Or perhaps the core was massive enough that it collapsed into a black hole instead. The answer remains uncertain, a reminder that even with modern telescopes and decades of observation, the universe still holds mysteries. The birth of a pulsar is thus a moment of extreme violence followed by an eternity of steadily decaying energy. The massive star collapses, rebounds, explodes, and at the center of the chaos, a neutron star begins its long, slow spin down, beaming energy into space, lighting up the surrounding debris and serving as a cosmic monument to the star that once was. These newborn pulsars are the universe's way of taking stellar ashes and forging something simultaneously dead and intensely alive. A corpse that shines, a remnant that radiates, a testament to the fact that even in death, stars can be beautiful. In the years following their discovery, astronomers accumulated observations of pulsars across the galaxy. Each new pulsar added to the growing understanding of what these objects were and how they behaved. Patterns began to emerge from the data, revealing the underlying physics that governed pulsar evolution. What started as a handful of mysterious radio sources became a diverse population of spinning neutron stars, each with its own characteristics but all following similar physical laws. The most immediately obvious property of any pulsar is its period, the time between successive pulses. The very first pulsar discovered, now designated PSR B19E19+21, has a period of 1.337 seconds. Others pulse much faster. The Crab pulsar's 33 millisecond period made it one of the faster pulsars known when it was discovered. And then, in 1982, astronomers found PSR B1937+21, a pulsar spinning at 641 times per second, completing a rotation every 1.6 milliseconds. This millisecond pulsar shattered expectations about how fast neutron stars could spin. At the other end of the spectrum, some pulsars have periods of several seconds. PSR J2 444 through 933 holds the record for the longest known period at 8.5 seconds between pulses. These slow pulsars are typically older objects that have lost much of their rotational energy over time. The range from milliseconds to seconds might not sound dramatic, but it represents an enormous variation in physical conditions. A pulsar spinning 600 times per second has a surface velocity near the speed of light, while a pulsar spinning once every few seconds is relatively leisurely by neutron star standards. But the period alone doesn't tell the whole story. What makes pulsars particularly interesting is how their periods change over time. Most pulsars are slowing down, their periods gradually lengthening as they lose rotational energy. This spin down is measurable with careful timing observations. For a typical pulsar, the period might increase by about 1 part in a million per year. That's an extraordinarily small change requiring years of precise observations to measure, but it's detectable and it's crucial for understanding pulsar evolution. The rate at which a pulsar slows down is described by something called the period derivative, usually written as p dot. This is simply the change in the period divided by the time interval over which the change is measured. A pulsar with a large period derivative is slowing down quickly. One with a small period derivative is slowing down very gradually. Young pulsars tend to have large period derivatives because they're still energetic and rapidly losing energy. Old pulsars have small period derivatives because they've already lost most of their energy and are slowly coasting toward quiescence. From the period and period derivative, astronomers can calculate several important quantities. One is the pulsar's characteristic age, an estimate of how long ago the pulsar was born. This is just the period divided by twice the period derivative, giving a rough timescale for the pulsar's evolution. The Crab pulsar, for example, has a characteristic age of about 1300 years, which matches well with the known date of the supernova that created it in 1054. Other pulsars have characteristic ages of millions or even tens of millions of years. Another crucial quantity is the magnetic field strength. Pulsars slow down primarily by radiating electromagnetic energy, and the rate of this energy loss depends on both the rotation rate and the magnetic field strength. By measuring how fast a pulsar is slowing down, astronomers can estimate the strength of its magnetic field. Typical pulsars have surface magnetic fields of around 1 trillion Gauss, about 100 billion times stronger than Earth's magnetic field. These are mind-bendingly strong fields, strong enough to dominate all of the physics in the pulsar's vicinity. The relationship between period and period derivative is often displayed in what's called a PP diagram, where P stands for period and the second P is for period derivative. If you plot all known pulsars on this diagram, with period on one axis and period derivative on the other, patterns appear. Most normal pulsars cluster in the upper right portion of the diagram. These are objects with periods of order 1 second and period derivatives indicating moderate to rapid spin down. These are the classic radio pulsars, objects that were born in supernovae and have been slowly spinning down ever since. But there's another population that appears in a completely different region of the diagram. Down in the lower left, with periods of just a few milliseconds and tiny period derivatives, sit the millisecond pulsars. These objects are spinning hundreds of times per second, yet slowing down so gradually that they'll continue spinning for billions of years. They're the cosmic marathon runners, patiently rotating long after their normal pulsar cousins have faded into silence. Their existence requires a different formation mechanism, one we'll explore in detail shortly. The energy being radiated away by a pulsar can be calculated from its period and period derivative. This energy, often called the spin-down luminosity, represents the rate at which the pulsar loses rotational energy. For young, energetic pulsars, this can be enormous. The Crab pulsar radiates about 100,000 times the total luminosity of our Sun, all of it coming from rotational energy. This energy goes into accelerating particles, generating electromagnetic radiation, and stirring up the surrounding nebula. It's visible across the spectrum from radio waves to gamma rays. As pulsars age, their spin-down luminosity decreases. They have less rotational energy to give away, and they're losing what remains more slowly. An old pulsar might radiate only a tiny fraction of the Sun's luminosity. Eventually, the energy drops below the threshold needed to maintain the emission mechanism, and the pulsar becomes undetectable. It continues to exist as a neutron star, still spinning, still possessing an enormous magnetic field, but no longer producing the beams that made it visible to us. The emission mechanism itself remains somewhat mysterious despite decades of study. We know that particles are accelerated to high energies somewhere in the pulsar's magnetosphere, the region surrounding the neutron star where the magnetic field dominates. These particles spiral along magnetic field lines and emit radiation, but the exact location where this happens, the precise physics of the acceleration, and the detailed processes that shape the beams are still subjects of active research. Several models have been proposed. In the polar cap model, particles are accelerated right at the magnetic poles on the neutron star surface. Electric fields pull particles away from the surface, accelerating them to high speeds in a narrow cone around the magnetic axis. In the outer gap model, acceleration happens far from the star, in gaps in the magnetosphere where the electric field can build up. These different models make different predictions about the emission properties, and astronomers continue to test them against observations. One fascinating aspect of pulsar emission is its broadband nature. The Crab pulsar, for example, pulses in radio waves, visible light, X-rays and gamma rays, all with the same period. This means the emission mechanism must operate across an enormous range of energies. The particles being accelerated must reach a wide spectrum of velocities, and the radiation processes must be efficient across all these wavelengths. Understanding how a single mechanism can produce such broad emission remains a challenge. The stability of pulsar periods makes them extraordinary natural clocks. The most stable pulsars, particularly the millisecond pulsars we'll discuss later, rival the best atomic clocks built by humans. Over years or decades of observation, their pulses arrive with such regularity that astronomers can predict the arrival time of any given pulse to within microseconds or even nanoseconds. This timing precision has made pulsars invaluable tools for testing fundamental physics. But pulsar timing isn't perfectly smooth. Occasionally, pulsars experience sudden speed-ups called glitches. The pulsar's rotation suddenly increases slightly, as if the star got a kick of extra rotational energy from somewhere. These glitches are thought to be caused by events in the neutron star's interior. The crust of a neutron star contains a lattice of nuclei, similar to the crystalline structure of ordinary matter but at much higher density. As the pulsar spins down, the crust adjusts and occasionally the strain becomes too great. The crust cracks, rearranges slightly, and transfers angular momentum to the rest of the star, causing the observed speed-up. The Vela pulsar is particularly prone to glitches, experiencing them every few years. After a glitch, the pulsar's rotation gradually returns toward its pre-glitch behavior, though often not quite reaching it before the next glitch occurs. Studying these glitches provides insights into the structure of neutron star interiors, one of the few ways we have to probe the physics at such extreme densities. Pulsars also show variations on longer timescales. Some change their pulse profiles, the detailed shape of their radio pulses over months or years. Some switch between different modes of emission, suddenly changing their average pulse shape or intensity. A few pulsars have been observed to turn off completely for periods ranging from minutes to years before turning back on. These intermittent pulsars add another layer of mystery to pulsar behavior, suggesting that the emission mechanism is more complex and variable than simple models would suggest. The interstellar medium through which pulsar signals travel affects the pulses in observable ways. As radio waves propagate through ionized gas, different frequencies travel at slightly different speeds. This dispersion causes lower frequency signals to arrive slightly delayed compared to higher frequencies. By measuring this delay across different radio frequencies, astronomers can calculate the dispersion measure, which tells them the integrated electron density along the line of sight to the pulsar. This, combined with models of the galaxy's electron distribution, allows estimation of the pulsar's distance. Distance measurements are crucial for mapping the three-dimensional distribution of pulsars in the galaxy. We now know that pulsars are concentrated in the galactic disk, particularly in the spiral arms where massive star formation occurs. This makes sense. Massive stars are born in spiral arms, and when they explode as supernovae, they leave neutron stars behind. The distribution of pulsars traces the distribution of their progenitor stars. Some pulsars, however, are found far from the galactic plane, high above or below the disk. These are typically older pulsars that have had time to wander away from their birthplaces. Neutron stars are often given a kick during the supernova explosion, a sudden acceleration that can send them flying through space at hundreds of kilometers per second. Over millions of years, this motion carries them far from the spiral arms where they were born. Some pulsars have such high velocities that they're escaping the galaxy entirely, destined to wander intergalactic space. The study of pulsar properties has revealed a diverse population of objects united by common physics, but displaying remarkable variety in details. From the rapidly spinning Crab pulsar energizing its surrounding nebula, to ancient millisecond pulsars keeping time with extraordinary precision, from pulsars that glitch regularly to those that blink on and off mysteriously. Each pulsar adds texture to our understanding of neutron stars. They're not simply identical objects stamped out by a cosmic factory. They're individuals, each with its own history, its own quirks, its own story to tell. And by listening carefully to their steady ticking, measuring their periods and period derivatives, studying their glitches and mode changes, astronomers continue to learn about physics in conditions that cannot be replicated anywhere else in the universe. In the early 1980s, pulsar astronomy seemed well understood. Pulsars were born in supernovae, spun rapidly at first, then gradually slowed down over millions of years until they became too faint to detect. The story was clean and coherent. Then, in 1982, astronomers discovered PSR B1937 plus 21, and the entire narrative became more interesting. This pulsar spun at 641 times per second, far faster than any pulsar previously known. To put this in perspective, imagine a city-sized object rotating so quickly that its surface moves at a significant fraction of light speed. The centrifugal force at the equator is enormous, nearly enough to tear the star apart, held in check only by the incredible gravity of the neutron star. Yet despite this frantic rotation, the pulsar was slowing down extraordinarily gradually. Its period derivative was tiny, suggesting it would continue spinning for billions of years. This discovery was revolutionary because it revealed a second pathway for creating pulsars. These millisecond pulsars, as they came to be called, weren't freshly born from supernova explosions. They were old neutron stars that had been spun back up to high speeds through a process called accretion. The key was that they existed in binary star systems. Here's how the recycling process works. Imagine a binary system containing two stars orbiting each other. One star is more massive than the other, and as the massive star evolves, it expands into a red giant and then explodes as a supernova, leaving behind a neutron star. The explosion might disrupt the binary, sending both objects flying off in different directions. But sometimes the system survives, remaining bound despite the violence of the supernova. Now the system consists of a neutron star and a normal star orbiting each other. The neutron star, if it was born as a normal pulsar, gradually spins down over millions of years. Its magnetic field weakens. Eventually it becomes an old, dead neutron star, spinning perhaps once per second, no longer emitting detectable beams. It seems destined for quiet obscurity. But then the companion star ages and begins to evolve. As it expands into a red giant, its outer layers can overflow what's called the Roche lobe, the region around each star where that star's gravity dominates. Material from the expanding companion begins to fall toward the neutron star. This accretion of matter transfers angular momentum to the neutron star, spinning it up. It's like taking an old record on a turntable and giving it a push, except the push continues for millions of years, steadily accelerating the rotation. The accreting material forms a disk around the neutron star before spiraling down to the surface. This accretion disk is hot, heated by friction and by the conversion of gravitational potential energy into thermal energy as matter falls inward. The disk glows in X-rays, making the system visible to X-ray telescopes. During this phase, the system is known as a low-mass X-ray binary if the companion star is relatively lightweight, or a high-mass X-ray binary if the companion is more massive. The accretion continues for millions of years, steadily spinning up the neutron star. The rotation accelerates from perhaps once per second to hundreds of times per second. The magnetic field, which had weakened over the neutron star's earlier life as a normal pulsar, remains relatively weak. This combination of rapid rotation and weak magnetic field is the signature of millisecond pulsars. Eventually the accretion phase ends. The companion star runs out of material to donate, or the geometry of the binary changes so that material no longer flows onto the neutron star. The accretion disk dissipates, the X-ray emission fades, and what remains is a neutron star spinning hundreds of times per second. The fast rotation generates electric fields strong enough to accelerate particles and produce beams once again. The recycled neutron star has become a millisecond pulsar. These millisecond pulsars have several distinctive properties. They spin rapidly, with periods typically between 1 and 10 milliseconds. They slow down very gradually, with period derivatives typically 1,000,000 times smaller than normal pulsars. Their magnetic fields are relatively weak, around 1,000,000,000 Gauss rather than 1,000,000,000,000 Gauss, and many, though not all, are found in binary systems with white dwarf companions, the remnants of the stars that donated material and spun them up. The discovery of millisecond pulsars explained several puzzles. Astronomers had found X-ray sources that seemed to contain neutron stars accreting matter from companion stars. The recycling theory predicted that these systems should eventually evolve into millisecond pulsars, and observations confirmed this. Some millisecond pulsars are still in the process of being spun up, showing both X-ray emission from ongoing accretion and radio pulsations. These transitional pulsars switch back and forth between accretion-powered and rotation-powered states, providing direct evidence of the recycling process. The extreme stability of millisecond pulsar rotation makes them exceptional timekeepers. Because they're spinning so fast and slowing down so gradually, their periods are extraordinarily stable. The best millisecond pulsars keep time as accurately as the best atomic clocks on Earth, and they do it naturally, without any intervention. Astronomers can predict the arrival time of pulses from these objects years in advance to within microseconds. This stability has made millisecond pulsars powerful tools for detecting gravitational waves, as we'll explore later. It has also made them useful for testing general relativity and studying the interstellar medium. and it raises interesting questions about just how fast neutron stars can spin before they tear themselves apart. There's a theoretical maximum rotation rate for neutron stars, determined by the balance between gravity pulling inward and centrifugal force pushing outward. If the star spins too fast, material at the equator will be flung off into space. The exact limit depends on the neutron star's mass and radius, which in turn depend on the equation of state of nuclear matter at extreme densities. Current estimates suggest the maximum spin rate is somewhere around 1,500 to 2,000 times per second, though no pulsar has been found spinning faster than about 700 times per second. Why don't we see pulsars spinning at the theoretical maximum? One possibility is that accreting neutron stars reach an equilibrium spin rate where the torque from accretion is balanced by the torque from their magnetic fields. As material falls onto the star, it tries to spin the star up, but the magnetic field threads through the accretion disk, and the interaction between field and disk creates a torque that opposes further spin-up. When these torques balance, the spin rate stabilizes. This equilibrium spin rate depends on the magnetic field strength and the accretion rate, and it typically falls in the range of a few hundred rotations per second, consistent with observed millisecond pulsar periods. Some millisecond pulsars exist in exotic binary systems. Black widow pulsars are paired with very low-mass companions, typically only a few % of the Sun's mass. The intense radiation from the pulsar heats the companion, causing it to evaporate. Over time, the pulsar is literally destroying its companion through its radiation output. The name comes from the black widow spider, where the female sometimes consumes the male after mating. In a few billion years, these systems may consist of solitary millisecond pulsars, having completely evaporated their companions. Redback pulsars are similar but have slightly more massive companions. These systems show dramatic variability as material from the companion sometimes blocks the pulsar emission. The complex interplay between the pulsar's radiation, the stellar wind from the companion, and the remaining accretion flow creates a messy, dynamic environment that astronomers are still working to understand. Some millisecond pulsars are in tight binary systems with other neutron stars. These double neutron star systems are particularly interesting because both objects contribute to the system's gravity, creating strong relativistic effects. The Hulse-Taylor pulsar, discovered in 1974, was the first such system found, and remains one of the most important for tests of general relativity. And then there are the isolated millisecond pulsars, spinning rapidly but without any visible companion. How did these objects get spun up if they're not in binary systems now? One possibility is that they were once in binaries, but the companion was completely evaporated, leaving the millisecond pulsar alone. Another is that the binary was disrupted by some interaction, perhaps with a third star, ejecting the companion and leaving the millisecond pulsar to wander solo through the galaxy. The population of millisecond pulsars continues to grow as surveys discover more of them. They are harder to find than normal pulsars in some ways because their rapid rotation means their pulses are very brief, requiring high time resolution to detect, but they're also more stable and longer lived. So once found, they can be studied for decades without significant changes in their properties. Millisecond pulsars represent nature's way of taking old worn-out neutron stars and giving them new life. The recycling process transforms objects that seem destined for obscurity into some of the most stable natural phenomena in the universe. They're testimony to the rich variety of evolutionary paths that stars can follow, and to the unexpected ways that binary interactions can reshape stellar remnants. From death to new life, from slow rotation to frantic spinning, from faded silence to renewed beaming, millisecond pulsars show that even in the realm of stellar corpses, there's room for rebirth and renewal. The universe is full of binary star systems, two stars bound together by gravity, orbiting their common center of mass. More than half of all stars exist in such partnerships, swinging around each other over periods ranging from hours to millions of years. When one or both of those stars evolves into something compact, a white dwarf, neutron star or black hole, the resulting binary system becomes a natural laboratory for testing physics in extreme conditions. Binary pulsars are systems where at least one of the components is a pulsar. The pulsar's regular ticking provides an extraordinarily precise clock, and by carefully timing the arrival of pulses, astronomers can measure the orbital motion with exquisite accuracy. These systems have yielded some of the most stringent tests of Einstein's general theory of relativity, revealed the existence of gravitational radiation, and provided insights into neutron star masses and the evolution of compact binaries. The story begins on September 2, 1974, when Russell Hulse and Joseph Taylor were using the Arecibo radio telescope in Puerto Rico to search for new pulsars. They found one, designated PSR B1913 plus 16, with a period of 59 milliseconds. Already interesting for its relatively fast spin, the pulsar became extraordinary when they continued observations. The period between pulsars wasn't constant. It varied in a regular pattern, speeding up and slowing down with a cycle of about 7 hours and 45 minutes. This variation wasn't due to any change in the pulsar's rotation. Rather, it was a Doppler effect. When the pulsar moved toward Earth in its orbit, the pulses arrived slightly more frequently. When it moved away, they arrived less frequently. The pulsar was in orbit around another object, completing one orbit every 7.75 hours. From the amplitude of the Doppler variations and applying Kepler's laws of orbital motion, Hulse and Taylor could determine that the companion had a mass similar to the Sun, and that the two objects were separated by less than the radius of the Sun. Given the short orbital period and the fact that the companion wasn't visible in optical or radio observations, it was almost certainly another neutron star. This was the first discovered double neutron star system, a truly remarkable find. Here were two stellar corpses, each the size of a city, locked in a tight orbital embrace, circling each other in less than 8 hours. The system provided an immediate test of general relativity. In Einstein's theory, gravity is not a force transmitted instantaneously across space, as Newton imagined. Rather, massive objects curve space-time, and other objects move along the resulting curved paths. When objects move in curved space-time, particularly when they accelerate as they do in orbit, the theory predicts that space-time itself should ripple, generating gravitational waves that carry energy away from the system. For the Hulse-Taylor pulsar, general relativity predicts that gravitational waves should carry away orbital energy, causing the two neutron stars to gradually spiral inward. The orbital period should shorten over time. This effect is tiny for most systems, completely unmeasurable. But the Hulse-Taylor system is compact and contains massive objects, making the effect large enough to detect with sufficiently precise timing. Hulse and Taylor, along with their colleagues, monitored the pulsar for years. The observations required extraordinary precision, accounting for the Earth's motion around the Sun, the telescope's location on the rotating Earth, propagation delays through the interstellar medium, and numerous other effects. But the effort paid off. The orbital period was indeed decreasing by about 76 microseconds per year. The two neutron stars were spiraling inward, exactly as general relativity predicted. The match between observation and theory was stunning. The observed rate of orbital decay agreed with general relativity's prediction to within a fraction of a percent. This was the first indirect detection of gravitational waves, providing strong evidence that these ripples in spacetime actually exist. For this discovery, Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. The implications were profound. General relativity had passed yet another test, this time in a regime of strong gravity and high velocities where Newtonian gravity would give very different predictions. The observations confirmed that gravitational radiation behaves exactly as Einstein's equations say it should, carrying energy and angular momentum away from accelerating masses, and they provided confidence that gravitational waves exist and could, in principle, be detected directly. The Hulse-Taylor pulsar remains under observation, and the orbital decay continues precisely as predicted. In about 300 million years, the two neutron stars will merge, creating either a more massive neutron star or collapsing into a black hole. The merger will produce a burst of gravitational waves and likely a brief but brilliant emission of light and other radiation, similar to the neutron-star mergers that have been observed through gravitational wave detectors and optical telescopes in recent years. Since the discovery of the Hulse-Taylor system, more binary pulsars have been found. The most remarkable is PSR J0737-3039, discovered in 2003. This system contains two pulsars, both visible from Earth, orbiting each other every 2.4 hours. Having two active pulsars in the same system is extraordinarily rare and extraordinarily useful. Each pulsar provides an independent clock, allowing even more precise measurements of the system's properties. The double pulsar system has enabled multiple tests of general relativity. Astronomers can measure the Shapiro delay, the extra time it takes light to traverse the curved spacetime near a massive object. As one pulsar passes behind the other from Earth's perspective, its radio signals travel through the curved spacetime near the companion, and this introduces a measurable delay. The size of this delay depends on the companion's mass, providing an independent way to measure neutron star masses. They can also measure relativistic spin precession, where the pulsar's spin axis slowly wobbles due to the curvature of spacetime. They can detect the advance of the peristron, the point of closest approach in the orbit, which shifts slightly with each orbit due to relativistic effects. Each of these measurements provides an independent test of general relativity, and in every case the theory passes with flying colours. Binary pulsars have also allowed precise measurements of neutron star masses. By carefully timing pulses and modelling the orbital motion, astronomers can determine the masses of both objects in the binary to high precision. Most neutron stars measured this way have masses between about 1.2 and 2 solar masses. The typical neutron star is around 1.4 times the mass of the Sun, but there's a range. The most massive neutron stars known have masses around 2 solar masses, PSR J1614-2230 and PSR J0348+0432. Both have measured masses very close to 2 solar masses. These massive neutron stars are important for constraining the equation of state of nuclear matter. If neutron stars can exist with masses this high without collapsing into black holes, it tells us something about how matter behaves at extreme densities. The physics must be stiff enough, provide enough pressure to support these massive objects against gravitational collapse. Some binary pulsars are in highly eccentric orbits, with the two objects swinging close together and then separating to much larger distances with each orbit. These eccentric binaries provide different tests of relativity than circular binaries. The varying separation means varying gravitational field strength, allowing astronomers to probe how physics changes with field strength. Other binaries have white dwarf companions rather than neutron star companions. These systems allow different types of measurements. White dwarfs are less massive than neutron stars but still provide measurable relativistic effects. And because white dwarfs can sometimes be seen in optical telescopes, astronomers can study them directly, measuring their properties independently of the pulsar timing observations. The study of binary pulsars has become a major subfield of pulsar astronomy. These systems are not just curiosities, they're precision instruments for testing fundamental physics, laboratories where gravity is strong enough that relativistic effects dominate, clocks accurate enough to measure effects that would be invisible in weaker gravitational fields. Every binary pulsar discovered adds to our understanding of neutron stars, gravity, and the evolution of compact objects. And the discoveries continue. Surveys keep finding new binary pulsars, each with its own particular properties. Some have unusual companion stars. Some have peculiar orbital characteristics. Some switch between different emission states. Each adds detail to the picture of how these systems form, evolve, and ultimately meet their fates in spectacular mergers. From Hulse-Taylor's pioneering discovery to today's population of dozens of known binary pulsars, these dancing pairs have illuminated corners of physics that would otherwise remain dark. For decades after the Hulse-Taylor discovery, gravitational waves remained tantalizingly indirect. Binary pulsars showed that orbital energy was being lost exactly as expected if gravitational waves were carrying it away, but no one had directly detected the waves themselves. Gravitational waves are incredibly weak, ripples in space-time so subtle that even the most violent cosmic events produce waves that stretch and squeeze distances by less than the width of a proton over kilometers. Then, on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves from merging black holes. This was a triumph of experimental physics, confirming Einstein's century-old prediction and opening a new way of observing the universe. But LIGO detects high-frequency gravitational waves, those produced by stellar mass objects merging in seconds. There's another regime of gravitational waves, much lower in frequency, that LIGO cannot access. And this is where pulsars enter the story once more. Imagine a supermassive black hole binary. Two black holes, each millions or billions of times the mass of the Sun, orbiting each other at the center of a galaxy. These monsters take thousands or millions of years to complete an orbit, and as they spiral together, they generate gravitational waves with frequencies of nanohertz, billionths of a hertz. These waves have wavelengths comparable to the size of the galaxy itself, and they pass through our local neighborhood of space constantly, a background hum of gravitational radiation from countless supermassive black hole binaries across the universe. Detecting such low-frequency waves requires an entirely different approach. You can't build a detector big enough to measure them directly. Instead, astronomers turn to nature's own detector, pulsars. Specifically, they use pulsar timing arrays, collections of millisecond pulsars spread across the sky that serve as the endpoints of a galaxy-scale gravitational wave detector. The concept is elegant. Millisecond pulsars, as we've discussed, are extraordinarily stable clocks. If you observe a millisecond pulsar for years, you can predict when each pulse should arrive to within microseconds or even nanoseconds. Now imagine a gravitational wave passing between Earth and a distant pulsar. The wave stretches and squeezes space itself, changing the distance between us and the pulsar very slightly. This change in distance alters the travel time of the pulsar's signals, causing pulses to arrive slightly earlier or later than expected. Any single pulsar could show timing variations for many reasons: changes in the interstellar medium, imperfections in our solar system models, undetected planets around the pulsar, or simple measurement noise. But if gravitational waves are passing through our region of space, they should affect multiple pulsars in a correlated way. The pattern of timing variations across many pulsars should follow a specific mathematical relationship called the Helling-Downs curve, named after the physicists who first calculated it in the 1980s. Pulsar timing arrays were proposed specifically to search for this gravitational wave background. Several collaborations formed to carry out the observations. The North American Nanohertz Observatory for Gravitational Waves, known as NanoGrav, uses radio telescopes in the United States and Canada. The European Pulsar Timing Array, or a PTA, uses European telescopes. The Parkes Pulsar Timing Array in Australia, called PPTA, uses the Parkes telescope. And the Indian Pulsar Timing Array, INPTA, uses Indian facilities. These collaborations also work together as the International Pulsar Timing Array, or EPTA, sharing data and coordinating observations. For more than 15 years, these groups observed dozens of millisecond pulsars, timing them with ever-increasing precision. They looked for correlations in timing residuals, the tiny differences between when pulses were observed and when they were predicted to arrive. They ruled out various sources of noise and systematic errors. They improved their models of solar system dynamics and interstellar propagation, and they waited for the signal to emerge from the noise. On June 29, 2023, multiple pulsar timing array collaborations simultaneously announced their results. After analyzing data spanning 15 to 20 years, they had found strong evidence for a gravitational wave background. The timing variations across different pulsars showed the correlations predicted by the Helling-Downs curve. The signal was there, hidden in years of accumulated timing data, finally rising above the noise threshold. This was the first detection of nanohertz gravitational waves, a completely different frequency regime than the waves detected by LIGO and other ground-based interferometers. The waves detected by pulsar timing arrays are produced by completely different sources, most likely the population of supermassive black hole binaries throughout the universe. Every major galaxy merger brings together the supermassive black holes from both galaxies, and these black holes gradually spiral together over millions of years, producing gravitational waves that propagate across the cosmos. The detected signal is consistent with the expected background from these supermassive black hole binaries. The amplitude and frequency spectrum match theoretical predictions reasonably well, but there's still much to learn. Can individual sources be identified, or is the signal entirely a stochastic background from countless unresolved binaries? Are there contributions from other sources, like cosmic strings or phase transitions in the early universe? How can the signal be used to constrain models of galaxy evolution and black hole demographics? Pulsar timing arrays are continuing to collect data, adding new pulsars to their datasets and improving timing precision. As more data accumulates, the signal will strengthen, allowing more detailed characterization. There's also the possibility of detecting individual supermassive black hole binaries if any are close and massive enough to stand out above the background. Such detections would provide unique information about specific systems, complementing what can be learned from the overall background. The 2023 announcement was a watershed moment, but it's really just the beginning of gravitational wave astronomy in the nanohertz regime. New telescopes coming online, like the Meerkat Array in South Africa and eventually the Square Kilometre Array, will allow even more sensitive timing observations. More pulsars will be added to timing arrays. Timing precision will improve. Over the next decade or two, pulsar timing arrays will map the gravitational wave sky in this low-frequency band, revealing details about supermassive black holes, galaxy mergers, and possibly exotic physics from the early universe. This achievement represents the culmination of work spanning decades. From the discovery of millisecond pulsars in the 1980s, through the development of high-precision timing techniques, through years of patient observation and data analysis, the pulsar timing community has built a detector unlike any other. It uses natural objects scattered across the galaxy as the components of an instrument that spans parsecs. It measures the subtle influence of gravitational waves on the fabric of space-time itself, and it does so by paying close attention to the clock-like ticking of stellar remnants, listening carefully as they count out the seconds and reveal the ripples passing through the cosmos. Pulsars, once a surprising discovery made by a curious graduate student, have become tools for probing the deepest mysteries of physics. They've revealed the nature of neutron stars, tested general relativity in extreme conditions, provided clocks of extraordinary precision, and now enabled the detection of gravitational waves from the universe's most massive objects. From radio signals on chart paper to ripples in spacetime, the journey of pulsar astronomy continues to surprise and enlighten. Globular clusters are ancient stellar cities, spherical collections of hundreds of thousands or even millions of stars packed into regions just tens of light years across. These clusters formed in the early universe more than 10 billion years ago, and they've remained bound together ever since, orbiting through the halos of galaxies. The stars in globular clusters are old, composed mostly of hydrogen and helium with very few heavier elements. They're relics of an earlier era of star formation, fossils that preserve information about the universe's youth. Within these dense stellar environments, pulsars appear in unexpected abundance. Despite the old age of globular cluster stars, which should long ago have exhausted their supply of massive stars capable of producing supernovae, and thus fresh pulsars, globular clusters contain dozens of known pulsars. Even more surprising, many of these are millisecond pulsars, and many are in binary systems. The density of pulsars in globular clusters, per unit volume, far exceeds that in the galactic disk. Something about the cluster environment is conducive to creating and maintaining these objects. The key is the high stellar density. In the core of a globular cluster, stars are packed thousands of times more closely than in the Sun's neighborhood. Close encounters between stars are relatively common. Stars can pass near each other, exchanging energy and momentum. More dramatically, stars can collide or gravitationally capture each other into binary systems, or disrupt existing binaries and rearrange their components. This stellar ballet creates a dynamically rich environment where binary systems form and evolve in ways that don't occur in the sparse field of the galaxy. Consider a neutron star in a globular cluster. Perhaps it was born in the cluster when the cluster was young and still contained massive stars. Or perhaps it was formed elsewhere and later captured by the cluster. Either way, it now finds itself in an environment where close encounters with other stars are possible. If the neutron star encounters a binary system containing a red giant or other evolved star, the interaction can result in the neutron star capturing the evolved star as a companion, or the original binary being disrupted and recombined in various ways. Once the neutron star is in a binary with an evolved companion, accretion can begin. The companion transfers mass onto the neutron star, spinning it up into a millisecond pulsar. This is the same recycling process that occurs in the galactic field, but in globular clusters, the formation of such binaries is greatly enhanced by the high stellar density. Old neutron stars that would otherwise remain dead are brought back to life through dynamical interactions that give them companions. Some globular clusters are particularly rich in pulsars. Terzen 5, a globular cluster in the constellation Sagittarius, contains more than 40 known pulsars despite being only about 20 light-years across. This is an extraordinary concentration. The cluster's high stellar density and large mass make it a pulsar factory, with ongoing dynamical interactions continuously creating and modifying binary systems. Another prolific cluster is 47 Tucanae, a bright globular cluster visible to the naked eye from the southern hemisphere. It contains more than 20 known pulsars, including several in exotic binary configurations. The cluster's proximity to Earth, about 13,000 light-years away, makes it an excellent target for detailed pulsar studies. Radio telescopes can observe individual pulsars in the cluster and track their orbits, their companions, and their emission properties with considerable precision. The binary systems found in globular clusters are often more exotic than those found in the galactic field. Many involve unusual companions, helium white dwarfs, main sequence stars, or even other neutron stars. Some binaries have been heavily modified by subsequent dynamical interactions, leading to eccentric orbits or unusual mass ratios. A few systems appear to be in the process of evolving, with ongoing mass transfer or recent interaction events that have altered their configurations. Exchange interactions are particularly interesting. Imagine a binary system containing a millisecond pulsar and a white dwarf companion orbiting each other peacefully. Another star passes by, approaching close enough that the gravitational interactions become significant. The intruder might capture the pulsar, ejecting the white dwarf and forming a new binary. Or it might eject the pulsar, capturing the white dwarf instead. Or all three objects might interact in complex ways, with the final outcome depending on their masses, velocities, and impact parameter. These interactions can create binaries that would be essentially impossible to form through normal stellar evolution. For example, a pulsar might end up paired with a main sequence star, even though the pulsar is far older than any main sequence star in the cluster. The binary was assembled through dynamics, not evolution. Such systems provide unique opportunities to study how neutron stars interact with different types of companions. Globular clusters also contain pulsar-pulsar binaries, systems where both components are neutron stars that happen to be pulsars. These are rare in the galactic field but more common in clusters due to the enhanced likelihood of forming exotic binaries through dynamical interactions. Having two pulsars in the same system allows extraordinarily precise measurements of orbital parameters and relativistic effects, similar to the double pulsar PSR J737 -3039 but formed through an entirely different process. The study of globular cluster pulsars requires specialized observational techniques. The pulsars are typically far away, making them fainter than many galactic field pulsars. They're also crowded together in a small region of sky, which can cause confusion and interference between signals. Radio telescopes need good sensitivity and excellent angular resolution to separate individual pulsars and track their properties. Searches for pulsars in globular clusters have been ongoing for decades, using telescopes like the Parkes Radio Telescope in Australia, the Green Bank Telescope in the United States, and the Arecibo Telescope in Puerto Rico before its collapse in 2020. These searches have discovered dozens of pulsars in clusters, with new detections continuing as instruments improve and search strategies become more sophisticated. One challenge is acceleration searching. Pulsars in globular clusters are moving within the cluster's gravitational potential, and if they're in binary systems, they're also orbiting their companions. Both of these motions introduce Doppler shifts that can smear out the pulsar signal, making detection difficult. Specialized search algorithms account for possible accelerations, effectively searching a multidimensional parameter space to find pulsars despite their complex motions. The discoveries have revealed surprising diversity. Some cluster pulsars have extremely short orbital periods, circling their companions in just a few hours. Others have wide orbits taking weeks or months. Some show evidence of recent interactions that have modified their binaries. A few are isolated, perhaps having lost companions in past interactions or having formed as isolated objects. Each system tells a story about the cluster's dynamical history. Timing observations of globular cluster pulsars face unique challenges. The pulsars are embedded in the cluster's potential well, experiencing gravitational fields from the cluster's overall mass distribution. These fields can introduce subtle timing effects that must be modeled accurately. The presence of many nearby stars means potential for additional undetected companions or perturbations from passing stars. And the interstellar medium within and around clusters can differ from the galactic field, affecting signal propagation. Despite these challenges, precise timing of cluster pulsars has yielded important results. Mass measurements of neutron stars in cluster binaries contribute to our understanding of the neutron star mass distribution. Orbital measurements constrain the history of binary interactions and exchange events. Studies of how pulsars are distributed within clusters inform models of cluster dynamics and evolution, and the sheer number of pulsars in some clusters makes them laboratories for statistical studies of pulsar properties and evolution. Some globular clusters show evidence of intermediate mass black holes lurking at their centers, objects with masses hundreds or thousands of times the Sun's mass. These are different from the stellar mass black holes formed in supernovae and the supermassive black holes found in galactic centers. If they exist, they would represent a missing link in black hole demographics. Pulsars orbiting near the cluster center could potentially feel the gravitational influence of such a black hole, providing indirect evidence for its presence through timing anomalies or unexpected orbital perturbations. The future of globular cluster pulsar astronomy looks promising. New telescopes with greater sensitivity will detect fainter pulsars, expanding the known populations in well-studied clusters and finding pulsars in clusters where none are currently known. Improved timing precision will enable better characterization of exotic binaries and more stringent tests of relativistic gravity in the cluster environment. And ongoing theoretical work will help interpret the observations, connecting what we see to the dynamical processes that created these systems. Globular clusters are thus stellar laboratories on two levels. They preserve information about the early universe through their ancient stellar populations, and they demonstrate what happens when stars and stellar remnants are packed closely enough that dynamical interactions dominate. The pulsars found in these dense stellar islands are products of this unique environment, cosmic survivors shaped by billions of years of close encounters, orbital dances, and occasional stellar collisions. They're reminders that the universe is not static, that even objects as dense and stable as neutron stars can be reshaped by their surroundings, and that in the crowded hearts of ancient stellar cities, anything that's gravitationally possible will eventually happen. While most pulsars fit into the broad categories we've discussed, there's a menagerie of unusual objects that defy easy classification. These exotic pulsars push the boundaries of what neutron stars can do, revealing phenomena that stretch our understanding of physics in extreme conditions. They're the outliers, the anomalies, the objects that make astronomers pause and wonder what else might be lurking in the data. Magnetars are perhaps the most extreme. These are neutron stars with magnetic fields so strong they beg a description. While typical pulsars have surface magnetic fields around 1 trillion Gauss, magnetars boast fields of 1 quadrillion Gauss or more, 1,000 times stronger still. These are the most intense magnetic fields known anywhere in the universe. The energy stored in a magnetar's magnetic field exceeds the object's rotational energy, making magnetars fundamentally different from rotation-powered pulsars. The magnetic field of a magnetar is strong enough to affect the structure of atoms, squashing electron clouds into elongated shapes and making chemistry impossible in any normal sense. The field is so intense that the quantum vacuum itself responds, exhibiting birefringence where light of different polarizations travels at different speeds. Near the surface of a magnetar, physics enters a regime that cannot be replicated in any terrestrial laboratory. Magnetars were first identified as a distinct class in the 1990s, though some had been observed earlier without being recognized as such. They emit strongly in X-rays powered not by rotation but by the decay of their magnetic fields. As the field gradually weakens over thousands of years, the energy released heats the neutron star and generates high-energy radiation. Some magnetars show dramatic outbursts where their X-ray emission suddenly increases by factors of hundreds or thousands, sometimes accompanied by the emission of giant flares that briefly outshine the entire rest of the galaxy in gamma rays. The cause of these outbursts is thought to be starquakes, sudden fractures in the neutron star's crust triggered by stresses from the intense magnetic field. When the crust cracks, magnetic field lines can suddenly reconnect, releasing enormous amounts of energy in a short burst. The largest magnetar flare ever recorded occurred on December 27, 2004, when the magnetar SGR 1806-20 released as much energy in 1/10 of a second as the Sun emits in 100,000 years. The burst of gamma rays and X-rays was so intense that it measurably affected Earth's ionosphere from 50,000 light-years away. Not all magnetars show the classic pulsar behavior of steady, regular pulses. Many are irregular, bursting unpredictably and showing erratic variations in their emission. This has led to confusion about whether they should be classified as pulsars at all, though they're clearly neutron stars and some do show periodic pulsations. The distinction between magnetars and pulsars has become somewhat blurred, with some objects showing characteristics of both categories. Intermittent pulsars are another curiosity. These objects turn on and off, sometimes switching between an active state where pulses are easily detected and a quiet state where they vanish entirely. The switching can occur on various timescales. Some intermittent pulsars flip states every few minutes or hours. Others might remain in one state for days or weeks before switching, and a few have been observed to stay quiet for years before suddenly turning back on. The cause of this intermittent behavior isn't fully understood. One possibility is that the emission mechanism is unstable, turning on and off as conditions in the magnetosphere change. Perhaps the flow of particles along magnetic field lines is sporadic, or the acceleration regions responsible for generating radio emission flicker in and out of existence. Another idea is that the pulsar's magnetic field or rotation axis is precessing, wobbling like a tilted spinning top, and this changes the geometry such that the emission beams sometimes point toward Earth and sometimes don't. PSR Beam 1931+24 is a well-studied intermittent pulsar. It spends about a week emitting detectable radio pulses, then turns off for about a month, then turns back on again. This pattern repeats regularly, suggesting a quasi-periodic mechanism. Observations show that when the pulsar is off at radio wavelengths, it's still spinning down as if it were emitting, implying that energy loss continues even when the radio emission ceases. This suggests the intermittency is specifically in the radio emission mechanism, not in the overall energetics. Rotating radio transients, abbreviated RATs, are related to intermittent pulsars but even more sporadic. These objects emit very brief, bright radio pulses separated by long intervals of silence. The pulses might occur once every few minutes, with nothing detectable in between. RATs were discovered by reanalyzing archival pulsar survey data, using new search techniques that look for isolated bright pulses rather than periodic signals. The nature of RATs is debated. They might be pulsars that emit normally but whose beams are so narrow or whose emission is so weak that we only occasionally catch a bright pulse when everything aligns just right. Or they might represent a different emission mode, where the pulsar only occasionally produces bursts of radio emission strong enough to detect, Some pulsars seem to transition between behaving like normal pulsars and behaving like RATs, suggesting the phenomena are related. X-ray pulsars are neutron stars detected primarily through their X-ray emission rather than radio waves. Many are in binary systems where they're accreting matter from a companion star, and the X-rays come from the hot material falling onto the neutron star's surface. As the material spirals down along magnetic field lines, it creates hot spots at the magnetic poles, and these hot spots rotate with the star, producing periodic X-ray pulses. These accretion-powered X-ray pulses are different from rotation-powered radio pulses in fundamental ways. Their energy source is the gravitational potential energy of infalling matter, not rotational kinetic energy. Their periods are typically longer, seconds to minutes rather than milliseconds to seconds, because they haven't been spun up to millisecond periods yet or because accretion has slowed them down. And their magnetic fields need to be strong enough to channel the accretion flow, but not so strong that they prevent accretion entirely. Some X-ray pulsars show remarkable period changes. If the accretion rate increases, the neutron star can spin up, its period shortening over months or years. If accretion decreases or stops, the period can lengthen. A few X-ray pulsars have been observed to switch between spin-up and spin-down, reflecting changes in how matter flows onto the star. This provides direct observational evidence of the recycling process that creates millisecond pulsars. Gamma-ray pulsars emit high-energy photons with energies millions to billions of times higher than visible light. The Fermi Gamma-ray Space Telescope, launched in 2008, has discovered more than 200 pulsars that emit gamma rays, many of which were not previously known from radio observations. Some gamma-ray pulsars emit primarily in gamma rays, with little or no radio emission, challenging the assumption that all rotation-powered pulsars should be radio sources. The gamma-ray emission from pulsars arises from particle acceleration to extremely high energies, likely in the outer magnetosphere far from the neutron star surface. The emission mechanism is different from radio emission, which comes from closer to the star. Understanding why some pulsars are radio loud while others are radio quiet but gamma-ray loud is an active area of research, with implications for models of pulsar magnetospheres and particle acceleration. And then there's the intriguing possible connection between some pulsars and fast radio bursts, or FRBs. These are brief, intense bursts of radio emission lasting just milliseconds, arriving from distant galaxies. Most FRBs are one-off events, never repeating, but some sources have been observed to produce multiple bursts. The origin of FRBs has been one of astronomy's great mysteries since their discovery in 2007. In April 2020, a bright radio burst was detected from within our own galaxy, specifically from the direction of the magnetar SGR 1935 plus 2154. The burst had characteristics similar to FRBs, but was much closer and thus much less energetic than typical FRBs. Subsequent observations showed that the magnetar was in an active state, emitting X-ray bursts. This suggested that at least some FRBs might originate from magnetars, perhaps during giant flares or other outbursts. The connection between magnetars and FRBs is still being explored. Not all FRBs need to come from magnetars, and many details remain unclear, but the 2020 observation provided the first clear link between a known type of neutron star and these mysterious bursts, suggesting that the extreme magnetic fields and energetic processes in magnetars can produce bursts visible across cosmic distances. The diversity of pulsar-like objects has expanded dramatically since the simple picture of rotation-powered radio pulsars from the 1960s. We now know of magnetars powered by magnetic decay, intermittent pulsars that flicker on and off, RATs that emit sporadically, X-ray pulsars powered by accretion, gamma-ray pulsars shining at the highest energies, and possible connections to fast radio bursts. Each category reveals different aspects of neutron star physics, different emission mechanisms, different evolutionary pathways. This diversity suggests that neutron stars can exist in many different states depending on their age, magnetic field, rotation rate, binary status, and accretion history. A single neutron star might transition between different states over its lifetime. perhaps being born as a classical radio pulsar, evolving into a magnetar-like state if its magnetic field is strong enough, entering an accretion phase if it has a companion, being recycled into a millisecond pulsar and ultimately fading into quiescence. The full picture of neutron star evolution is complex, with many pathways and many outcomes. Astronomers continue to discover new types of unusual pulsars and pulsar-like objects. Each discovery adds to the rich collection of behaviors that neutron stars can exhibit, pushing theoretical models to accommodate new phenomena and revealing the full range of physics possible in these compact objects. The extreme zoo of exotic pulsars is a testament to the universe's creativity, showing that even within the narrow confines of neutron star parameter space, nature finds countless ways to surprise us. Beyond their value for fundamental physics and astrophysics, pulsars have potential practical applications. One of the most intriguing is spacecraft navigation. Current interplanetary spacecraft navigate using radio signals transmitted from Earth. Ground stations track the spacecraft's position and velocity by measuring signal travel times and Doppler shifts, and mission controllers use this information to calculate trajectories and plan maneuvers. But this Earth-based approach has limitations. As spacecraft travel farther from Earth, communication delays become significant. Commands sent to a spacecraft near Mars take several minutes to arrive, and replies take several minutes to return. For spacecraft in the outer solar system or beyond, delays can be hours or even days. This makes real-time navigation impossible. Everything must be planned in advance, with no immediate feedback. Moreover, the precision of Earth-based tracking degrades with distance. Measuring a spacecraft's position to within meters or kilometers is straightforward when it's in Earth orbit, but becomes challenging when the spacecraft is billions of kilometers away. Uncertainties accumulate and trajectory predictions become less accurate. For missions to the outer solar system or into interstellar space, these uncertainties can be significant. Pulsars offer an alternative. Because they're extraordinarily precise natural clocks scattered throughout the galaxy, spacecraft could potentially use pulsar signals for autonomous navigation. The idea is conceptually simple. If you know the positions of several pulsars and can detect their pulses, you can determine your position in space by comparing the pulse arrival times to predictions. Here's how it would work. Each pulsar's rotation period is known to high precision from years of Earth-based observations. If you're at a specific location in space, pulses from different pulsars will arrive with specific timing relationships depending on your position. If you're closer to one pulsar and farther from another compared to Earth, the relative arrival times of pulses from those two pulsars will be different from what observers on Earth see. By observing multiple pulsars simultaneously and comparing pulse arrival times, a spacecraft could triangulate its position in three-dimensional space, similar to how GPS receivers on Earth use signals from multiple satellites. The key advantage is that this would work anywhere in the solar system, or even in interstellar space without requiring communication with Earth. The spacecraft could navigate autonomously, determining its position and velocity using only the natural pulsar signals it receives. The concept isn't entirely new. The Pioneer 10 and 11 spacecraft launched in the 1970s carried plaques showing the positions of pulsars relative to the Sun. These plaques were designed as messages for any extraterrestrial civilization that might someday encounter the spacecraft, using pulsars as cosmic landmarks to indicate where and when the probes came from. But using pulsars for active navigation requires actually detecting and timing the pulsar signals on board the spacecraft, which is more challenging. The main technical challenge is detector sensitivity. Pulsar signals are weak, requiring large collecting areas and sensitive receivers to detect reliably. Earth-based radio telescopes use dish antennas tens or hundreds of meters across to observe pulsars. Building something that large on a spacecraft isn't feasible. But pulsars also emit X-rays, and X-ray detectors can be much smaller and lighter than radio antennas. In 2017, NASA demonstrated X-ray pulsar navigation using the Neutron Star Interior Composition Explorer, abbreviated NOSIR, an X-ray telescope mounted on the International Space Station. NICER observed several millisecond pulsars that emit strongly in X-rays, particularly PSR B1821-24 in the globular cluster Messier 28. By timing the arrival of X-ray pulses from this and other pulsars, the NASA team determined the space station's position to within a few kilometers, proving that X-ray pulsar navigation is feasible. This demonstration was an important milestone. It showed that the required technology exists and can work with realistic detector sizes and spacecraft power budgets. Future deep space missions could carry X-ray detectors specifically designed for pulsar navigation, allowing them to determine their positions autonomously without relying on Earth-based tracking. This would be particularly valuable for missions beyond the orbit of Saturn, where communication delays and tracking uncertainties become significant. Pulsar navigation could also enable new types of missions. Spacecraft exploring the outer solar system could coordinate their positions precisely without needing constant contact with Earth. Multiple spacecraft could work together, forming constellations or interferometer arrays, with each spacecraft knowing its position relative to the others. Missions to the very edge of the solar system or into the interstellar medium could navigate autonomously, even when communication with Earth becomes sporadic or impossible. Pulsars have also contributed to another area of discovery: exoplanets. The first confirmed planets outside our solar system were detected orbiting a pulsar, not a normal star. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of 2 planets orbiting PSR B1257 plus 12, a millisecond pulsar about 1,000 light-years away. This was a surprising find, as planets weren't expected to survive the supernova explosion that created the pulsar. The discovery was made through timing observations. As the pulsar orbits the common center of mass with its planets, its motion introduces Doppler shifts that change the observed pulsar arrival times in a periodic way. By carefully analyzing these timing variations, Wolszczan and Frail determined that the pulsar had at least 2 planets, with a third planet later confirmed through additional observations. The planets have masses comparable to Earth and orbit the pulsar at distances similar to the inner planets of our solar system. How these planets formed is still debated. They might be second-generation planets that formed from a debris disk left over from the supernova explosion, or they might be the remnants of a companion star that was destroyed, with the debris coalescing into planets. Either way, their existence demonstrates that planets can exist in extremely hostile environments, orbiting objects nothing like our Sun. Since then, a handful of other pulsar planetary systems have been found, though they remain rare compared to planets around normal stars. Pulsars are extremely precise clocks, making them sensitive to tiny orbital perturbations, so the fact that few pulsar planets have been detected likely means such systems are genuinely uncommon, rather than being difficult to detect. Pulsars have also been used to study the interstellar medium, the thin gas that fills the space between stars. As pulsar signals propagate through this gas, they're affected in measurable ways. The dispersion of radio waves mentioned earlier allows measurement of the electron density along the line of sight. Scintillation, the twinkling of pulsar signals analogous to the twinkling of starlight, provides information about turbulence in the interstellar medium. And Faraday rotation, the twisting of polarized radio waves by magnetic fields in the ionized gas, allows mapping of interstellar magnetic fields. By studying many pulsars in different directions, astronomers have built up 3-dimensional maps of electron density and magnetic fields in the galaxy. These maps reveal the structure of the interstellar medium, showing where gas is dense and where it's sparse, where magnetic fields are strong and where they're weak. This information is crucial for understanding how the galaxy evolves, how stars form, and how cosmic rays propagate. Pulsars serve as distant beacons for studying gravitational lensing. When light from a pulsar passes close to a massive object like a galaxy or galaxy cluster, the light is bent by the object's gravity, following curved paths through space-time. This gravitational lensing can cause multiple images of the pulsar to appear, or can magnify or distort the pulsar's signal. By studying these lensing effects, astronomers can measure the masses of the lensing objects and probe the distribution of dark matter. The study of pulsar polarization provides insights into both the pulsars themselves and the intervening medium. Pulsar radio emission is often highly polarized, with the electric field oscillating in a preferred direction. The polarization can change across the pulse profile, tracing the magnetic field structure in the emission region. And as the polarized signal propagates through the interstellar medium, interactions with magnetic fields cause the polarization angle to rotate, an effect that can be measured and used to study interstellar fields. Pulsars have even been proposed as navigational aids for future crewed missions to Mars or beyond. Astronauts on long-duration missions could use pulsar timing to determine their position independently of Earth, providing redundancy for spacecraft systems and ensuring that navigation remains possible even if communication is lost. While this application is still speculative, the feasibility has been demonstrated, and the technology continues to develop. From navigation aids to planet hosts, from interstellar probes to gravitational lenses, pulsars serve purposes far beyond the scientific curiosity that motivated their initial study. They're practical tools, cosmic lighthouses that illuminate not just astrophysical phenomena, but potential pathways for human exploration and technological development. These applications demonstrate that pure science, research driven by curiosity about how nature works, often yields unexpected practical benefits. The study of pulsars, begun because astronomers noticed something odd on a chart recording, has blossomed into a field with implications for fundamental physics, astronomy, and potentially even human spaceflight. The discovery of new pulsars requires sensitive telescopes, clever search algorithms, and often considerable patience. Despite decades of pulsar astronomy, surveys continue to find new objects, and each new pulsar adds to our understanding of the neutron star population. Modern pulsar searches employ sophisticated techniques to sift through vast amounts of data, searching for the telltale periodic signals buried in noise. Radio telescopes remain the primary instruments for finding pulsars. The giant dish at Arecibo, before its collapse in 2020, discovered hundreds of pulsars over its lifetime. The Parkes telescope in Australia has been a workhorse of pulsar astronomy, conducting numerous surveys and finding many of the known pulsars in the southern hemisphere. The Green Bank telescope in the United States continues this tradition, regularly discovering new objects. And new facilities are coming online with even greater sensitivity. The 500-meter aperture spherical radio telescope, known as FAST, located in a natural depression in the mountains of southwest China, is the world's largest single-dish radio telescope. With its enormous collecting area, FAST can detect fainter pulsars than any previous instrument. Since beginning scientific observations in 2016, FAST has discovered hundreds of new pulsars, including many with interesting properties: fair-spinning millisecond pulsars, pulsars in binary systems, pulsars in globular clusters. The telescope's sensitivity allows it to find objects that would have been invisible to earlier generations of instruments. Meerkat, an array of 64 radio dishes in South Africa, represents a different approach. Rather than a single large dish, Meerkat uses many smaller dishes working together as an interferometer. This design provides both sensitivity and excellent angular resolution, allowing the telescope to pinpoint the positions of pulsars precisely and to search regions of sky that are crowded with sources. Meerkat has already made important pulsar discoveries and will continue to do so for years. Looking further ahead, the Square Kilometre Array, or SKA, will be the most powerful radio telescope ever built when it's completed in the coming decades. As its name suggests, the SKA will have a total collecting area of 1 square kilometre, distributed across thousands of individual antennas spread over vast distances. The SKA will have unprecedented sensitivity for detecting faint pulsars, and its large field of view will allow it to survey huge swathes of sky efficiently. Estimates suggest the SKA could eventually find tens of thousands of new pulsars, perhaps doubling or tripling the known population. Finding pulsars in survey data is challenging. A typical survey observation collects data from a patch of sky, recording the intensity of radio emission as a function of time and frequency. If a pulsar is present, its periodic signal should appear in this data, but the signal is often weak, buried in noise from the receiver, from interference, from the sky itself. Extracting the signal requires careful processing. The standard approach uses something called a Fourier transform to convert the time series data into a frequency spectrum. If a periodic signal is present, it will appear as a peak in the spectrum at the corresponding frequency. Searching for peaks in the Fourier spectrum can reveal pulsars, but this only works if the pulsar is isolated and its signal isn't smeared out by dispersion or acceleration. Dispersion, the frequency-dependent delay introduced by the interstellar medium, can smear out pulsar signals across the observation. To compensate, search algorithms try many different dispersion measures, effectively de-dispersing the data at various trial values and checking whether a periodic signal appears. This multiplies the computational effort, as each possible dispersion measure requires reprocessing the entire dataset. Modern searches try hundreds or thousands of dispersion measures, searching a large parameter space to find hidden pulsars. Acceleration searching adds another dimension. If a pulsar is in a binary system, its orbital motion introduces Doppler shifts that can smear out the signal over long observations. To detect such pulsars, searchers must account for possible accelerations, trying various values and looking for signals that appear when the right acceleration is applied. This further increases the computational burden, but it also finds pulsars that would otherwise be missed. Machine learning has recently been applied to pulsar searching. Traditional search pipelines generate many candidate signals, most of which are false positives caused by interference, glitches in the instrumentation, or random noise fluctuations. Distinguishing real pulsars from these false positives requires human inspection, with astronomers looking at plots of candidates and deciding which are worth following up. This is time-consuming, and it's easy to miss interesting objects in the flood of candidates. Machine learning algorithms can be trained to recognize the signatures of real pulsars versus false positives, automating much of this classification. By training on known pulsars and known interference signals, the algorithms learn to identify characteristics that distinguish genuine detections. This speeds up searches, allows more candidates to be examined, and can improve the detection rate. Several recent pulsar discoveries have been made using machine learning-assisted pipelines. Once a pulsar candidate is identified, follow-up observations are necessary to confirm it. The pulsar needs to be reobserved to verify that the signal persists and comes from the same position in the sky. Its properties must be measured: period, period derivative, dispersion measure, flux density, pulse profile. If it's in a binary, the orbital parameters need to be determined. This characterization takes time, but is essential for understanding what type of object has been found. Some of the most interesting pulsar discoveries come from targeting specific types of sources. For example, astronomers have searched for pulsars in supernova remnants, since young neutron stars should often be found there. Several have been discovered this way, including pulsars in famous remnants like Vela, Crab and others. These young pulsars provide insights into neutron star birth and early evolution. Searchers have also targeted globular clusters, where the high stellar density makes pulsar formation through dynamical interactions likely. As discussed earlier, clusters like Terzan 5 and Fortissvan Tucanae have yielded dozens of pulsars. Dedicated surveys of clusters continue to find new objects, expanding the sample and revealing more about how pulsars behave in these dense environments. Unidentified gamma-ray sources detected by the Fermi telescope are another fruitful target. Many gamma-ray sources have no obvious counterpart at other wavelengths, and some turn out to be pulsars that are bright in gamma rays, but faint or absent at radio wavelengths. By searching the radio sky at the positions of unidentified gamma-ray sources, astronomers have discovered several gamma-ray pulsars that would have been missed in blind radio surveys. Citizen science has even played a role in pulsar discovery. The Einstein Home Project uses volunteers' computers to process pulsar search data during idle time, harnessing distributed computing power to search for faint signals in vast datasets. Several pulsars have been discovered through Einstein Home, demonstrating that public participation can contribute to frontier science. The population of known pulsars now numbers in the thousands, and that number continues to grow. Each new discovery adds statistical weight to studies of pulsar properties, helps map the distribution of neutron stars in the galaxy, and occasionally reveals an object with unusual or extreme characteristics that challenges existing models. The ongoing surveys, powered by ever more sensitive telescopes and sophisticated data analysis techniques, ensure that pulsar astronomy remains a vibrant field with regular discoveries. Looking ahead, the next generation of radio telescopes will transform our view of the pulsar population. The SKA, when complete, will have the sensitivity to detect pulsars in other galaxies, not just our own Milky Way. It will find pulsars so faint that they're currently invisible. It will probe regions of the galaxy that have been difficult to search due to confusion or absorption. And it will discover rare objects, pulsars orbiting black holes, pulsars with unusual companions, pulsars in exotic states that haven't been seen before. These future discoveries will depend not just on telescope sensitivity, but on continued development of search algorithms, data processing infrastructure, and theoretical models to interpret the observations. The data volumes will be staggering, requiring advanced computing and storage capabilities. But the scientific rewards will be substantial, advancing our understanding of neutron stars, testing physics in extreme conditions, and perhaps revealing phenomena that we haven't yet imagined. From Jocelyn Bell's careful examination of chart recordings in the 1960s to modern automated pipelines processing terabytes of data from sensitive radio arrays, the search for pulsars has evolved dramatically. Yet the core excitement remains the same, the thrill of detecting a new cosmic lighthouse, of adding another data point to our understanding of the universe, of discovering something no one has seen before. And as long as there are telescopes listening to the sky, astronomers will continue searching, knowing that somewhere in the radio noise new pulsars are waiting to be found. Pulsar astronomy has transformed our understanding of the universe in ways that extend far beyond the objects themselves. These spinning neutron stars have become tools for addressing fundamental questions about physics, gravity, and the nature of matter. They've provided tests of theories that would be impossible to perform in any terrestrial laboratory. And they've revealed phenomena that were predicted but never observed until pulsars made them accessible. The impact on our understanding of neutron stars is profound. Before pulsars were discovered, neutron stars were a theoretical prediction, interesting but unconfirmed. The discovery immediately validated decades of theoretical work on stellar evolution and supernova explosions. It confirmed that matter could exist in the extreme state predicted by Landau and others, compressed to nuclear density and supported against further collapse by quantum degeneracy pressure. Since then, pulsar observations have constrained the properties of neutron stars with increasing precision. Mass measurements from binary pulsars have shown that neutron stars typically have masses between 1.2 and 2 solar masses, with a fairly narrow distribution. This constrains models of supernova explosions and core collapse. The existence of neutron stars with masses approaching 2 solar masses tells us that the equation of state of nuclear matter must be relatively stiff, providing enough pressure to support these massive objects. The equation of state describes how matter behaves at extreme densities, relating pressure to density. Different theoretical models predict different equations of state, and measuring the masses and radii of neutron stars can distinguish between these models. Unfortunately, measuring neutron star radii is difficult. Pulsars don't have well-defined surfaces in the way normal stars do, and their small sizes and large distances make direct radius measurements challenging. But observations of X-ray emission from neutron star surfaces, combined with mass measurements from pulsar timing, are beginning to constrain radii and thus the equation of state. The gravitational wave detections from merging neutron stars provide additional constraints. When LIGO and Virgo detected gravitational waves from the merger of 2 neutron stars in August 2017, the signal contained information about how the neutron stars deformed as they spiraled together. This tidal deformability depends on the equation of state. A stiff equation of state produces less deformable neutron stars, while a soft equation of state allows more deformation. The gravitational wave data favored relatively soft equations of state, complementing what's learned from pulsar observations. Together, pulsar timing, X-ray observations, and gravitational wave detections are converging on a consistent picture of neutron star structure. The core likely contains primarily neutrons, with a smaller number of protons and electrons to maintain charge neutrality. There may be exotic particles like hyperons or strange quarks in the very centre, where densities are highest. The outer layers consist of neutron-rich nuclei arranged in a crystalline lattice, with the nuclei becoming increasingly neutron-rich at greater depths. The surface has a thin atmosphere of normal matter. Pulsars have been essential for testing general relativity in the strong field regime. Einstein's theory makes specific predictions about how objects move in curved spacetime, how gravitational waves are emitted, and how time flows in strong gravitational fields. Binary pulsars provide natural laboratories where these predictions can be tested. The Hulse-Taylor pulsar demonstrated that gravitational waves carry energy away from orbiting masses, exactly as predicted. The double pulsar system PSR J0737-3039 has enabled multiple independent tests of relativity, each confirming the theory's predictions with remarkable precision. Other binary pulsars have measured relativistic effects like the Shapiro delay and periastron advance, again finding agreement with general relativity. These tests are important because they probe regimes where gravity is much stronger than anything we can achieve on Earth or in the solar system. The neutron stars in binary pulsars create gravitational fields that curve spacetime significantly. Objects move at appreciable fractions of the speed of light. Under these conditions, general relativity makes predictions that differ substantially from Newtonian gravity, and the differences can be measured. Every test that confirms general relativity strengthens our confidence that the theory correctly describes gravity even in extreme conditions. Alternative theories of gravity have been proposed over the years, theories that make slightly different predictions than general relativity. Binary pulsars allow these alternatives to be tested. Most have been ruled out or severely constrained by pulsar observations. General relativity remains the theory that best describes all available data, from subtle orbital effects in binary pulsars to the gravitational wave signals from merging black holes. Pulsars have also contributed to our understanding of fundamental constants and their possible variation. Some theories suggest that the constants of nature, things like the gravitational constant or the fine structure constant, might change slowly over cosmic time. If this were true, it would have observable effects on pulsar timing. The periods of pulsars depend on these constants, and if the constants were changing, pulsar periods would evolve differently than expected. Decades of pulsar timing data have found no evidence for variation in fundamental constants. The precision of millisecond pulsar timing is sufficient that even tiny changes would be detectable, yet none have been seen. This places strong constraints on how much fundamental constants can vary, if at all. The universe appears to be governed by laws that remain constant over time, at least over the millions of years that pulsar timing can probe. The impact extends to cosmology as well. Pulsars provide independent measurements of distances and velocities that can be compared with other methods. Pulsar dispersion measures, combined with models of the galaxy's electron distribution, give distance estimates that complement parallax measurements and other techniques. Pulsar proper motions, the angular movement across the sky, combined with distances give three-dimensional velocities that help map the dynamics of the galaxy. And as we've discussed, pulsar timing arrays are now detecting the gravitational wave background from supermassive black hole binaries, opening a new window on galaxy evolution and cosmic structure. This detection method complements ground-based gravitational wave observatories, accessing different frequency ranges and different source populations. Together, these observations are building a complete picture of gravitational waves across the cosmos. The study of pulsars has also driven technological development. The need for precise timing has led to improvements in atomic clocks and time standards. The algorithms developed for pulsar searching have applications in signal processing more broadly. The computational techniques for handling large data sets have influenced how astronomers approach data-intensive problems in other areas, and the development of sensitive radio receivers for pulsar observations has benefited radio astronomy as a whole. Perhaps most importantly, pulsars have demonstrated the value of serendipity in science. Jocelyn Bell wasn't searching for pulsars when she found them. She was studying quasars, and the discovery came from paying attention to an anomaly that could easily have been dismissed as interference. The history of pulsar astronomy is full of unexpected discoveries. The first millisecond pulsar, the first binary pulsar, magnetars, the pulsar planets. Each came as a surprise, revealing phenomena that hadn't been predicted or imagined. This is a reminder that exploration-driven science, research that doesn't have a specific application in mind but simply seeks to understand how nature works, often yields the most profound and unexpected insights. The practical applications of pulsars, from spacecraft navigation to gravitational wave detection, weren't motivations for the original discovery. They emerged later as understanding deepened and new possibilities became apparent. Looking back over more than 50 years of pulsar astronomy, the field has matured from a curiosity to a sophisticated discipline, with deep connections to physics, astronomy, and technology. Pulsars have illuminated the depths of massive stars, the properties of matter at extreme densities, the nature of gravity and strong fields, and the ripples in space-time from cosmic collisions. They've shown us that the universe is more inventive than we imagined, capable of producing phenomena that stretch our understanding and challenge our assumptions. And yet, despite all we've learned, pulsars still hold mysteries. We don't fully understand their emission mechanisms. We don't know all the details of their interior structure. We can't predict which neutron stars will be visible as pulsars and which won't. We haven't found all the types of pulsars that might exist. The field continues to evolve, driven by new observations, new theoretical insights, and new questions that emerge as old puzzles are solved. The quiet revolution that began with scruff-on-chart recordings continues. Each new pulsar discovered, each precise timing observation, each test of relativity, adds to the edifice of knowledge that pulsar astronomers have built. The work is painstaking, often requiring years of observations to extract meaningful results. But the payoff is a deeper understanding of the universe at its most extreme, where matter is compressed beyond recognition, where gravity warps the flow of time, and where nature demonstrates what's possible when physics is pushed to its limits. These models. Unfortunately, measuring neutron star radii is difficult. Pulsars don't have well-defined surfaces in the way normal stars do, and their small sizes and large distances make direct radius measurements challenging. But observations of X-ray emission from neutron star surfaces, combined with mass measurements from pulsar timing, are beginning to constrain radii and thus the equation of state. The gravitational wave detections from merging neutron stars provide additional constraints. When LIGO and Virgo detected gravitational waves from the merger of two neutron stars in August 2017, the signal contained information about how the neutron stars deformed as they spiraled together. This tidal deformability depends on the equation of state. A stiff equation of state produces less deformable neutron stars, while a soft equation of state allows more deformation. The gravitational wave data favored relatively soft equations of state, complementing what's learned from pulsar observations. Together, pulsar timing, X-ray observations, and gravitational wave detections are converging on a consistent picture of neutron star structure. The core likely contains primarily neutrons, with a smaller number of protons and electrons to maintain charge neutrality. There may be exotic particles like hyperons or strange quarks in the very center, where densities are highest. The outer layers consist of neutron-rich nuclei arranged in a crystalline lattice, with the nuclei becoming increasingly neutron-rich at greater depths. The surface has a thin atmosphere of normal matter. Pulsars have been essential for testing general relativity in the strong field regime. Einstein's theory makes specific predictions about how objects move in curved spacetime, how gravitational waves are emitted, and how time flows in strong gravitational fields. Binary pulsars provide natural laboratories where these predictions can be tested. The Hulse-Taylor pulsar demonstrated that gravitational waves carry energy away from orbiting masses, exactly as predicted. The double pulsar system PSR J0737-3039 has enabled multiple independent tests of relativity, each confirming the theory's predictions with remarkable precision. Other binary pulsars have measured relativistic effects like the Shapiro delay and periastron advance. again finding agreement with general relativity. These tests are important because they probe regimes where gravity is much stronger than anything we can achieve on Earth or in the solar system. The neutron stars in binary pulsars create gravitational fields that curve space-time significantly. Objects move at appreciable fractions of the speed of light. Under these conditions, general relativity makes predictions that differ substantially from Newtonian gravity, and the differences can be measured. Every test that confirms general relativity strengthens our confidence that the theory correctly describes gravity even in extreme conditions. Alternative theories of gravity have been proposed over the years, theories that make slightly different predictions than general relativity. Binary pulsars allow these alternatives to be tested. Most have been ruled out or severely constrained by pulsar observations. General relativity remains the theory that best describes all available data, from subtle orbital effects in binary pulsars to the gravitational wave signals from merging black holes. Pulsars have also contributed to our understanding of fundamental constants and their possible variation. Some theories suggest that the constants of nature, things like the gravitational constant or the fine structure constant, might change slowly over cosmic time. If this were true, it would have observable effects on pulsar timing. The periods of pulsars depend on these constants, and if the constants were changing, pulsar periods would evolve differently than expected. Decades of pulsar timing data have found no evidence for variation in fundamental constants. The precision of millisecond pulsar timing is sufficient that even tiny changes would be detectable, yet none have been seen. This places strong constraints on how much fundamental constants can vary, if at all. The universe appears to be governed by laws that remain constant over time, at least over the millions of years that pulsar timing can probe. The impact extends to cosmology as well. Pulsars provide independent measurements of distances and velocities that can be compared with other methods. Pulsar dispersion measures, combined with models of the galaxy's electron distribution, give distance estimates that complement parallax measurements and other techniques. Pulsar proper motions, the angular movement across the sky, combined with distances give three-dimensional velocities that help map the dynamics of the galaxy. And as we've discussed, pulsar timing arrays are now detecting the gravitational wave background from supermassive black hole binaries, opening a new window on galaxy evolution and cosmic structure. This detection method complements ground-based gravitational wave observatories, accessing different frequency ranges and different source populations. Together, these observations are building a complete picture of gravitational waves across the cosmos. The study of pulsars has also driven technological development. The need for precise timing has led to improvements in atomic clocks and time standards. The algorithms developed for pulsar searching have applications in signal processing more broadly. The computational techniques for handling large data sets have influenced how astronomers approach data-intensive problems in other areas, and the development of sensitive radio receivers for pulsar observations has benefited radio astronomy as a whole. Perhaps most importantly, pulsars have demonstrated the value of serendipity in science. Jocelyn Bell wasn't searching for pulsars when she found them. She was studying quasars, and the discovery came from paying attention to an anomaly that could easily have been dismissed as interference. The history of pulsar astronomy is full of unexpected discoveries. The first millisecond pulsar, the first binary pulsar, magnetars, the pulsar planets. Each came as a surprise, revealing phenomena that hadn't been predicted or imagined. This is a reminder that exploration-driven science, research that doesn't have a specific application in mind but simply seeks to understand how nature works, often yields the most profound and unexpected insights. The practical applications of pulsars, from spacecraft navigation to gravitational wave detection, weren't motivations for the original discovery. They emerged later as understanding deepened and new possibilities became apparent. Looking back over more than 50 years of pulsar astronomy, the field has matured from a curiosity to a sophisticated discipline, with deep connections to physics, astronomy, and technology. Pulsars have illuminated the depths of massive stars, the properties of matter at extreme densities, the nature of gravity in strong fields, and the ripples in space-time from cosmic collisions. They've shown us that the universe is more inventive than we imagined, capable of producing phenomena that stretch our understanding and challenge our assumptions. And yet, despite all we've learned, pulsars still hold mysteries. We don't fully understand their emission mechanisms. We don't know all the details of their interior structure. We can't predict which neutron stars will be visible as pulsars and which won't. We haven't found all the types of pulsars that might exist. The field continues to evolve, driven by new observations, new theoretical insights, and new questions that emerge as old puzzles are solved. The quiet revolution that began with scruff on chart recordings continues. Each new pulsar discovered, each precise timing observation, each test of relativity adds to the edifice of knowledge that pulsar astronomers have built. The work is painstaking, often requiring years of observations to extract meaningful results. But the payoff is a deeper understanding of the universe at its most extreme, where matter is compressed beyond recognition, where gravity warps the flow of time, and where nature demonstrates what's possible when physics is pushed to its limits. As we drift toward the end of our journey through pulsar astronomy, it's worth reflecting on where the field has been and where it might go. From a graduate student's curiosity about unusual signals to a mature discipline that spans fundamental physics, astrophysics, and even engineering applications, pulsar science has come remarkably far in just over 5 decades. The legacy of pulsar discovery extends beyond the objects themselves. The techniques developed for finding and studying pulsars have influenced how astronomers approach time-domain astronomy more broadly. The careful attention to periodic signals, the methods for searching vast datasets, the precision timing techniques that can measure intervals to nanoseconds, all of these have applications beyond pulsars. They've been adapted for studying other variable astronomical sources and have informed how astronomers think about signals hidden in noise. The interdisciplinary nature of pulsar research has brought together observers, theorists, and instrumentalists in productive collaborations. Understanding pulsars requires expertise in nuclear physics, plasma physics, general relativity, stellar evolution, observational astronomy, and signal processing. Few fields in astronomy require such diverse knowledge, and the synthesis of these different perspectives has enriched the science. Education and outreach have benefited from pulsars as well. The objects are conceptually accessible, spinning neutron stars beaming radiation like lighthouses, yet they connect to deep physics. This makes them excellent vehicles for teaching about extreme states of matter, about how science progresses through observation and theory working together, and about the rich variety of phenomena the universe contains. Many people have been drawn to astronomy through learning about pulsars, captivated by the idea of stellar corpses that pulse with clockwork regularity. The coming years promise continued excitement. The next generation of radio telescopes, particularly the square-kilometre array, will dramatically increase the known pulsar population and find objects that are currently too faint to detect. These new discoveries will include rare systems, pulsars in tighter binaries, pulsars with more massive companions, perhaps even a pulsar orbiting a black hole. A pulsar black hole binary would be an extraordinary discovery. No such system has been definitively found, though several candidates exist. Such a system would provide the ultimate test of general relativity, with the pulsar's precise timing measurements revealing the effects of the black hole's strong gravity. It could also provide information about black hole mass and spin, complementing what's learned from gravitational wave observations and X-ray studies. The continuing operation of pulsar timing arrays will refine the gravitational wave background detection and may lead to identification of individual supermassive black hole binaries. As more pulsars are added to timing arrays and observations extend over longer baselines, the sensitivity will improve. Within the next decade or two, astronomers may be able to pinpoint specific sources of low-frequency gravitational waves, observing individual merging supermassive black holes and studying their evolution. Space-based missions may also contribute. While X-ray pulsar navigation has been demonstrated, dedicated spacecraft carrying optimized instrumentation could push the technique further, enabling autonomous navigation for deep space missions. Future crewed missions to Mars or beyond might rely on pulsar timing for navigation, providing independence from Earth-based tracking systems. Theoretical work will continue to grapple with open questions about pulsar physics. What exactly happens in the magnetosphere to produce the radio emission? Why do some pulsars pulse at radio wavelengths while others are radio quiet? What causes intermittent emission and mode switching? How do magnetomagnetic fields decay, and what triggers their dramatic outbursts? These questions require both better observations and deeper theoretical understanding. The connection between pulsars and other neutron star phenomena will likely become clearer. As observations improve, the boundaries between different types of neutron stars, pulsars, magnetars, X-ray binaries, and so on may blur or sharpen, revealing the full spectrum of neutron star behavior. Understanding how a single object can transition between different states over its lifetime will provide insights into neutron star evolution. Multi-messenger astronomy, combining observations across different channels like electromagnetic radiation, gravitational waves, and neutrinos, will increasingly involve pulsars. The 2017 observation of a neutron star merger combined gravitational wave detection with optical, X-ray, and gamma-ray observations, revealing a wealth of information about the event. While that particular merger didn't involve pulsars, future events might, and pulsar timing arrays will contribute to the gravitational wave component of such observations. Citizen science may play a growing role. As datasets become larger and more complex, automated algorithms will handle most of the processing. But human pattern recognition remains valuable for identifying unusual or unexpected signals. Projects that engage the public in searching for pulsars or analyzing pulsar data can both contribute to science and help educate people about astronomy and the scientific process. The philosophical implications of pulsar astronomy deserve mention as well. These objects are reminders of the transience and transformation that characterize the universe. Stars that once shone steadily for millions of years end their lives in violent explosions, leaving behind remnants so dense and strange that they challenge our intuitions about matter and space. These remnants then evolve, sometimes being recycled into new active phases, sometimes fading into darkness, always following the inexorable laws of physics. Pulsars also remind us of the power of curiosity-driven research. The discovery came from a student paying attention to something odd, from a willingness to investigate the unexplained rather than dismissing it as noise. The subsequent development of the field has been driven largely by the intrinsic interest of the phenomena, by scientists wanting to understand how these objects work and what they can tell us about physics. The practical applications came later, emerging naturally from deepening understanding, and pulsars illustrate the interconnectedness of scientific knowledge. Understanding them required insights from nuclear physics, quantum mechanics, general relativity, electromagnetism, stellar evolution, and observational astronomy. No single discipline could have made sense of pulsars alone. Their study has been inherently interdisciplinary, drawing on the full range of physical sciences and in turn contributing back to those disciplines. As we lie here in the quiet darkness, thinking about pulsars spinning in the void, it's humbling to realize how much we've learned and how much remains unknown. These objects are simultaneously familiar and alien. They obey the same laws of physics that govern falling apples and orbiting planets, yet they exist in conditions so extreme that our everyday experience provides no guide. They're natural laboratories, cosmic gifts that allow us to test our theories in regimes we could never access otherwise. The story of pulsars is far from over. New chapters are being written with each observation, each discovery, each refinement of theory. The objects that surprised Jocelyn Bell in 1967 continue to surprise us today, revealing new phenomena, testing our understanding, and occasionally reminding us that the universe is more intricate and beautiful than we imagined. Thank you for joining me on this gentle drift through the story of pulsars. We've travelled from the first mysterious signals on chart paper through the realization that these are spinning neutron stars born in supernovae, across the diverse population of millisecond pulsars and binary systems, and into the modern era where pulsars help detect gravitational waves and test fundamental physics. We've met cosmic lighthouses spinning hundreds of times per second, magnetars with fields so strong they warp space itself, and stellar corpses recycled into new life through accretion. These objects, each just 20 kilometers across, contain more mass than our Sun. They spin with the precision of atomic clocks. They beam radiation across light years of space, and they've taught us about matter, gravity, and time in ways that would have been impossible without them. From stellar death comes extraordinary structure. From chaos emerges precise rhythm. From the extreme emerges understanding. If you've enjoyed this peaceful exploration of pulsars and their remarkable story, a like and subscribe would mean a great deal. It helps this channel continue bringing you these relaxing journeys through science and the cosmos. And for those of you already subscribed, thank you. Your support makes these videos possible. Whether you're still awake, drifting peacefully, or already deep in dreams, I hope you found something here worth carrying with you. The universe is vast and filled with wonders, and pulsars are among its most extraordinary creations. Spinning remnants of dead stars, keeping perfect time, sending their signals across the galaxy. Cosmic lighthouses marking the depths of space, reminding us that even in darkness, there are always beacons to guide us home. Rest well. The pulsars will keep spinning, keep ticking, keep beaming their light into the cosmos, and when you wake, they'll still be there, patient and precise, waiting for anyone who cares to listen.